show one example motivating that where these indices pick up, I think they, by and large, they do something reasonable. So what is shown here on the top left plot, you're seeing the climatological Z500, that these are the gray lines. Then I took a location over Greenland and identified all the days where this particular blocking index picks up, and then composited the Z500 with respect to those days. And you see the cyclonic wave breaking, like Taya talked to us about yesterday. So that is actually picked up. So these, when blocking occurs over Greenland, we get this sort of event. On the right-hand side are the composites for the surface impacts. So over much of Europe, it is actually this sort of Greenland blocking that gives us the lowest temperature extremes. And on the other hand, you get advection on the of warm air over Greenland itself. You can also see these surface contours. These are these surface pressure composites showing that this sort of blocking is closely related to the NAO. And just as an aside, if you look at time series of blocking, mostly what stands out to me is a lot of variability and a small trend. So there may be some exceptions, and I look forward to Jacob's talk, for example, later about the summer Greenland case. But where I've looked, mostly these time series look like this, but obviously we need to watch this. Also, these indices, they can pick out extreme events. So we got a lot of Greenland blocking in 2010. I remember this very well. 2010 was the year I moved to the UK, and for me, that was definitely an extreme event. Now, coming to evaluation of how blocking is represented in models, I will be showing summary evaluations for what we call physical climate models, so models that have a land surface, an ocean, an atmosphere, and sea ice, but they're not fully developed system models, so they don't have the full carbon cycle, for example. And these models, they have undergone generations of development, starting actually with AMIP models that don't have an ocean, and then through these several CMIP generations. I would also like, in the context of blocking, I'd like to highlight high-res MIP, which is one of the sub-MIPs of CMIP 6, where the community got together to increase the resolution both in the atmosphere and ocean. So that's illustrated by these scatter plots. So we see that for CMIP 5, ocean resolution was typically around 100 kilometers and between 1 and 200 in the atmosphere. Actually, that hasn't changed all that much for the bulk of the models going to CMIP 6. But then there is this concerted effort here, taking both the ocean and atmosphere resolution in some models to 25 kilometers or so. Now, this is going 30 years or so back and looking at an evaluation of AMIP models. So we can see that the models underestimate blocking frequency. This is a long-standing problem. So the dashed line here is the reanalysis. And again, also we see a lot of spread across the models. And then I'm now going forward to the most recent generations of models. And I will use an evaluation with this 2D index that I introduced before. And I have a Pacific sector and an Atlantic sector. And then I can calculate measures of performance across these two sectors, comparing the model with the reanalysis. So that's what's done on these plots. And let me walk you through it. So the metric I'm choosing is the root mean square error on the y-axis. And then there are different sets of models on the horizontal. So so there's a set of CMIP 5 models, of CMIP 6 models. And then I have two sets of models that are from the CMIP 6 high-res MIP models. So I squeezed these models into what I call low resolution coupled. So this mixes atmosphere and ocean, and high resolution coupled models. And then the last plot here is to give an idea of internal variability. So this is a root mean square error. So you could think, okay, I want a perfect model to have 0 root mean square error, but then variability comes in. So in fact, because you have a finite sample, you won't get to 0. And the estimate how far you could get, again, for model simulations is this one. So a model that cannot be distinguished from reanalysis would be somewhere here. So if we then start looking at this case of the Atlantic in winter, we do see an improvement going from CMIP 5 to CMIP 6, but also we see that biases remain. And there's also a small improvement with the for the high-risk MIP models. And the situation is actually fairly similar for other cases. So this is the Atlantic case in summer, where we get similar sort of improvement. If I go now to the Pacific, I would say the Pacific winter case really looks quite good. We are fairly close to the reanalysis with some of these models. And we also get some improvement in the Pacific in summer case. The blocking biases are smaller in the most recent generation of models, but biases also clearly remain. There are two more things to say about this plot. One is that this spread between models is actually quite large. So if you investigate a problem or if you have an application that depends on blocking, unfortunately, it matters which GCM you're using. So the best models are now in better agreement with the reanalysis than with the worst models. And another thing to say about this, I haven't investigated this systematically, but if you look at some of these colors here that represent different models. So here, for example, we have this yellow model, which performs very well in winter. Then if you go to summer, it's more like a middle of the road model. And similarly here, the inverse is happening for this blue model here. So unfortunately, we don't have consistency in blocking for performance across the models. So I'd like to extend this a bit from just using one blocking index or two that were behind the study and look at other metrics of how the mid-latitude circulation is represented in models. And this is from a paper led by Ben Harvey at Reading. And what is shown here on the top left is one of these classical metrics of storm activity-based, a variance-based metric from sea level pressure. And then what he did, he went back all the way to CMIP3 with that metric and calculated biases in CMIP3, CMIP5, and CMIP6 in how the storm track is represented. And similar to the blocking analysis I just presented, you do see these biases across the CMIP generations, but you also see that they become smaller as you move to CMIP6. Similar, not quite as strong, but a similar result you can also obtain if you look aloft at the zonal winds. By and large, still the biases decrease. So we know that blocking is related to other features of the mid-latitude circulation, to what we sometimes loosely call the mean state. And indeed, these results that there's some improvement in the blocking, they're also consistent with the fact that the mean state looks better in the models. So I borrowed this list from the review led by Tim Bullings, listing all the different factors that can play a role and that can improve blocking in models. So these can be increases in resolution, both in the atmosphere and ocean. And through resolution, orography, and in the ocean, we can get smaller SST biases. Vertical resolution can help, and both improved physics and model dynamics. What I've done until now, I've shown these very aggregate CMIP results that give you the integrated results from all these different factors, or you could say it confounds all these factors. So in high-res MIP, we still mix a few things. We mix resolution, but through the resolution, we get a better representation of orography, and we also get a reduction of SST biases. So I want to pick this last point up, the reduction of SST biases, show an example of that, and then show a few examples for these other things that can be done and have been done to improve blocking in models. So here's a highlight result from this paper by Athanasiadis et al., looking again at the set of high-risk MIP models, but now looking specifically of the role of SST biases for blocking performance in these models. And it's a very detailed study, and I'm just trying to give the upshot here from a detailed analysis. What is shown on the top is the difference in the SST bias between a set of low resolution and high resolution ocean models. What happens in the North Atlantic is that the low resolution models, they have a cold bias in this region. And because there's a cold bias in these low resolution models, you get too strong a regional gradient. So temperature decreases too quickly going from the equator to the pole. What is then shown in the study is that translates to the atmosphere. You get too much baroclinicity, too intense storm track, and too little blocking over Europe. And that's what is shown in this plot down here. So definitely getting rid of SST bias in coupled models is one thing that helps for the representation of blocking. So then an obvious next question is it all just SST biases? Are we done if we have models where these biases are eliminated? And I don't have a perfect plot to answer this, but I have one. So what is shown here, it's similar to these plots I showed before. It's again the high-risk MIP models shown against atmosphere resolution in this case. And on the left panel here, it's for the coupled models, and on the right panel here, it's for the corresponding AMIP models. And if you look at this result here, you see that the AMIP models, they are broadly where the best coupled models are, but they are not perfect. So they're still, and that's shown by this red arrow, you want to be down here. So there are still biases even in the AMIP models where you prescribe the observed SSTs. So no, eliminating SST biases doesn't fully get there. You can think about this in different ways. So you could say, okay, it's just intrinsic biases in the atmosphere model. Or you could think about it, okay, maybe there's something about the coupling itself. Maybe I need to represent RC interactions to represent blocking well. And for that, I don't have a multi-model answer, but I have one example. This is a study led by Paolo Davini, and he looked at one particular of the high-risk MIP models, the ECMWF IFS model, and compared that with seasonal forecasts from the same model. There's a lot going on in this plot. Let's look at this Central European case here. Black are the observations, and then going from these green lines to these blue lines is going from the low resolution high-risk MIP models to the high resolution high-risk MIP models. So you get some improvement. And then these purple lines next to it, that's the seasonal forecast model. And interestingly, you don't get any more improvement in blocking. And the difference between the seasonal forecast and the free running model is that the SST biases, they are not developed in the seasonal forecast model, but you do have RC interaction. So that would mean it's really, in this case at least, it's intrinsic biases in the atmospheric model that are behind this. So the answer is no, certainly for one case. Intrinsic atmosphere biases still remain important in the most latest generation of models. So I've discretely moved now from free running climate models to initialized predictions. And I'm staying with the ECMWF and another study with the ECMWF model by Jung et al. And I don't expect you to read through this long table, but what this details is all the different changes that were made to the seasonal forecasting system by ECMWF between around 2005 and 2008. And this mixes many different things, so changes to the parameterizations, to the diffusion. And of course, if this changes every few months, you don't have a clean assessment of which one of these changes led to a particular change in model performance, like blocking, for example. But what the authors did here in the study, then they reran 40 years of reforecasts with the seasonal prediction model. And then they could actually pinpoint what improved the blocking as all these changes were made. And two things came out. It was orographic drag, and it was the convection scheme, which is very interesting because this is a result from 2010. And I think since 2010, our understanding of the role of moist diabatic processes for blocking has improved very much and is very consistent with this early result. And also note that we have a session on these processes later today in the meeting. I was looking for then going to even shorter forecasts to the medium range. I was looking for a study to summarize like the long-term evolution of medium range prediction skill. I couldn't quite find that as a first order proxy. Maybe I went to the Tighe Museum and I had a look at blocking frequency in the different medium range forecast systems around about 15 years ago and in the very recent years. This is the blocking frequency 5 days ahead. And you can see just in terms of frequency, the models do an okay job. Some are struggling a bit sometimes, and maybe, this is not a formal analysis, maybe they are doing a bit better now in the most recent years. So this, either I didn't look properly, or perhaps this is a bit of a gap in the literature that we don't have this long-term view on the medium range blocking skill. And the last study I would like to show is one where for the Met Office medium range forecast system, this study by Martinez Alvarado and et al. They investigated a change to the dynamical core of the model. And unlike this multi-model results, which we don't seem to quite have, individual centers, they have a good track of their performance, and they showed controlling for other factors like resolution, that this improved blocking performance, leading to higher blocking frequency. And I'm showing this example because, again, it takes a bit of a multivariate view on blocking performance. So it shows the blocking index, but it also shows other dynamically relevant quantities like the ridge area defined here, which is maintained for longer. It's tended to have a negative bias in the earlier generation of model. And also another metric that can be used is a PV gradient at the tropopause, which again gets improved by this change. Before I conclude, I would like to go back to climate and show the projections across the different CMIP generations actually. And it's fairly quickly to present because we see a reduction of blocking everywhere. And we also see fairly good agreement by the models. I should also say this reduction is not very large. So we are going here, again, looking at Europe. I tried to work this out before. I think in this index, we are at between 10 and 15% of blocking frequency. And that goes down in the strongest scenario by about, I think it's 2-3% or something by the end of the century. So we see a modest reduction in blocking across the models and across winter and summer as well. So I'd like to finish up. So I asked this question, are we getting there? This representing blocking in models. And this phrase to get there, it's used in different ways, like, for example, talking to students and writing. Sometimes the emphasis can be on, oh, yes, we are getting there, we're making progress. And sometimes they say the same thing, or we say the same thing, but the emphasis is more on, we are not there yet, really, we are getting there. And I'm afraid we are still in this situation for blocking as well. So we've seen that over the last 30 years, blocking performance in weather and climate models has slowly improved due to parameterization development, increases in resolution, both in the atmosphere and ocean. A bit of a loose statement here, but I'd say some models are now not so bad. And when I say that, I mean compared to spread between models, or also compared to internal variability over the decades that we evaluate models. Multi-model projections, they agree on a decline in blocking frequency. It's relatively small if you compare it to internal variability. I think we have seen some examples telling us that we are not there yet. So models continue to underestimate blocking, and intrinsic atmosphere biases are part of that. Spread between models is very large. And model performance is not always consistent. So I showed this example for winter and summer performance of the same models, and it's very difficult to engineer a priori. So the best modeling centers putting together all the best ingredients may not have perfect blocking, even in this day. And then there's a whole point, I'm not sure I've come to something very sensible to say about this, but we are seeing this model agreement, but does it really give us confidence in view of all these issues? And yeah, that's the end of the talk. Thank you very much.
Yeah, we're gonna, like other days, leave questions to the end, but we are a little ahead of time. So if anyone has a question, yeah, please.
Hello, yeah. So my name is Prasad. I'm from Victoria University of Wellington, New Zealand. So my question is, you said that spread between model is large. So it is like, in multi-model ensemble you're talking about, or like the generations of the model, like CMIP 3, CMIP 5, CMIP 6, something like that?
So I mean the spread in the performance for blocking, say, across the CMIP 5 or the CMIP 6 ensemble, or even the high-risk MIP models. So just different models do differently well for blocking.
Okay. And about the high-risk MIP models, you said that it's an improvement. I just wanted to ask, are we observing an improvement for both the seasons, like summer, winter? And if yes, like how much? It's let's say like satisfied, or like are we still have to buckle up?
So I mean, the quantitative result depends on the index, and
Yeah.
so there's one version on the plots I showed. I think qualitatively, I'd say it's more the latter. So it got better, but it's not good enough.
Okay. Yep. Thank you.
We'll take more questions at the end, so save them for them. Thank you. Okay, so our next speaker is Mingyu Park on seasonal prediction of wintertime Pacific blocking.
Good morning, everyone. I'm Mingyu Park. I'm from Princeton University and GFDL. So in this talk, I'll present about seasonal prediction of wintertime North Pacific blocking by using GFDL seasonal forecast system. So as we discussed already yesterday, blocking has been extensively studied, partly because of its linkage to many different surface extremes. And one of the examples for winter blocking is cold extreme. The illustration here depicts one of the blocking type, omega-shaped blocking over the Central Europe. And we often see low temperature anomalies developed at the eastern flank of the blocking systems, as indicated by the blue dashed line here. And this downstream influence of blocking contributes to the occurrence of cold extremes over many different populated regions. So a specific example I brought here is North American cold anomalies induced by wintertime North Pacific blocking. So corresponding to cold temperature advection, Alaska and northwestern Canada, located at the downstream of the North Pacific blocking events, undergo significant cold anomalies. And this linkage is well captured by seasonal model forecast. So the right panel shows the same temperature composite from the GFDL Spear hindcast with no lead months. And we can see that the temperature anomalies associated with this North Pacific blocking are reproduced by the seasonal hindcast in an excellent quality. So the implication here is that as far as model captures the North Pacific blocking frequency well, its downstream impact is also likely to be well represented in seasonal hindcast. Then the question naturally follows is about how skillful we can predict the wintertime North Pacific blocking frequency using seasonal hindcast. And we use GFDL Spear modeling system to address this question. So GFDL Spear is a coupled climate model optimized for seasonal to multi-decadal climate prediction and projection. It is comprised of 50-kilometer resolution for the atmosphere and land components, and 1 degree for sea ice and ocean components. So with this modeling system, we generate a seasonal forecast every month. So this forecast system has currently 15 ensemble members since 1991 that are initialized on the first day of each month and integrated for 12 months afterwards. So regarding the blocking detection, we adapted the hybrid approach. It is a bit different from the reversal gradient approach that Dr. Reinhard introduced. It captures persistent quasi-stationary blocking systems retaining both meridionally reversed gradients and large amplitudes above certain threshold. And the analyzed period is 1991 to 2021 Surrey boreal winters. Okay, jumping into the result, we first investigate the wintertime blocking climatology. Top panel shows ERA5, the middle panel shows a pyramid large ensemble, and the bottom panel shows a SIM6 multimodal mean. Consistent with previous studies, approximately 200 out of 2,700 days in the analyzed period are blocked over the North Pacific Ocean. And we can also see that the Spear large ensemble has a very similar climatology compared to that of SIM6 multimodal mean. So in general, climate models overestimate the North Pacific blocking frequency and underestimate the North Atlantic blocking frequency. And the previous studies attributed the spatial modal biases to various sources, including the modal biases in atmospheric mean state, SST, and also errors in parameterization scheme and misrepresentation of transient eddy activity, as discussed in the previous talk. Okay, the main target of this study is seasonal prediction skill. So utilizing this December initialization output, we first look at the DJF blocking climatology in this hindcast. And compared to the blocking climatology in the free large ensemble simulations, the biases are weaker in magnitudes, but the spatial biases are still similar to the large ensemble simulations. And regarding the prediction skill, which is the main focus of this study, the panel here shows the map of anomaly correlation coefficient, which is one of the popular skill metric. And we see that overall good skills primarily found over the North Pacific Ocean, Greenland, and Northern Europe. However, when we consider lead months, this prediction skill sharply drops, even in lead month 1. So the bottom panels now show the same climatology and prediction skill, but with the November 1st initialization. And we see that the climatology largely remains the same as in December 1st initialization, but the prediction skill now becomes moderate. And this result is consistent with Davini et al. 2021, which used ECMWF seasonal forecast with 1 month lead. And they also found a small rank correlation skill for the North Pacific high latitude blocking. So going back to the high prediction skills found in the Western North Pacific Ocean when there is no lead months, it is natural to ask why this region has such high skills. And there are 2 main reasons we suggest. And the first reason is the properties of the low-level jet and the storm track, such as the intensity and location, are rectified by initial conditions in December initialization, which helps simulating the blocking onset variability. And secondly, ENSO teleconnection provided by initial conditions also play an important role in simulating this teleconnection-driven blocking anomalies on the seasonal timescale. To be specific on the first point, if we examine the composites of lower tropospheric winds for the first 5 days of December, from December 1st initialization during high blocking winters and low blocking winters, then their difference suggests that differences in intensity and the location of the low-level jet are well captured from December 1st initialization output, simulating this anticyclonic circulation feature in the background state. However, if we examine the same composites but using initializations in lead time, the background state in 2 subsets of winters are more close to its model climatology, resulting in a much weaker differences between the 2. Looking at this in a different angle, if we examine the Western North Pacific domain average low-level winds, then during high blocking winters, these contrasting features of jet intensity and location are well captured, well distinguished in the December 1st initialization, but that's not the case if there's a lead time in forecast initialization. And we see the same behavior if we look at the lower tropospheric the heat flux. So basically, it's saying that the meridional displacement of storm track eddy during high and low blocking winters is barely distinguished if there is a lead time in forecast initialization, resulting in a poor representation of synoptic scale eddy feedback onto the blocking variability. Okay, next point is about ENSO being a useful predictor of seasonal North Pacific blocking variability. The result here shows the rank correlation scale, another scale metric between the sphere blocking with no lead months and ERA5 blocking. And we see again that the substantial skills over the North Pacific Ocean, but with the northwest and southeast tilted structure, which resembles the ENSO teleconnection simulated by sphere. So we found that the Nino 3.4 index is well correlated with the North Pacific blocking frequency in both realities and sphere. So prompted by this finding, we test the hypothesis that seasonal prediction based on the ENSO blocking relationship might be more skillful for longer lead months. To use this observed ENSO blocking relationship, we construct a hybrid statistical dynamical model based on the linear multivariate regression. And also prompted by some theoretical backgrounds, we use the two predictors, Nino 3.4 and upstream precipitation from sphere hindcast with different initialization months. And the regression coefficients in the hybrid model are derived by regressing the hindcast Nino 3.4 index and upstream precipitation at late 0 months onto the observed North Pacific blocking frequency. So in doing so, we can utilize the observed blocking relationship and the observed relationship between ENSO and blocking, and also make a seasonal prediction based on the thermodynamic predictors. The reason we use upstream precipitation as a predictor of the North Pacific blocking is because it provides significant prediction skill. And mechanistically, I think we will discuss more in the next session. Steinfeld-Fall showed that the upstream latent heating also significantly contributes to the formation and the amplification of blocking through this divergent outflow. And then if we look at the linkage between the observed North Pacific blocking frequency and the precipitation as a metric of the latent heating, we see that the Okhotsk-Sea region, the enhanced Okhotsk-Sea region precipitation is associated with the North Pacific blocking. And that linkage is well captured by the sphere model with no lead time. So therefore, we use this ENSO Nino 3.4 index and upstream precipitation with lead time to make a hybrid forecast blocking. And the answer to the hypothesis is yes. The hybrid dynamical statistical model provides higher prediction skills for longer lead months. The result here is a December initialization when there is no lead month. And the left is hybrid model blocking correlation skill. The right one is a dynamical forecast correlation skill. And we see that with no lead time, correlation skills are comparable. With lead months, however, as we have seen before, the dynamical forecast substantially has low prediction skill over the North Pacific Ocean, some over Central Pacific due to remaining ENSO information. In contrast, the hybrid model prediction skill largely remains sustained over the entire North Pacific Ocean, which is encouraging. And then we found that this correlation skill of hybrid model is well maintained until lead months is up to 7. And this is due to more skillful prediction of ENSO up to a year and some skillful prediction of upstream precipitation to several months in this seasonal forecast. So with these results, we suggest that some prediction skills of North Pacific blocking frequency are possible beyond the 1 month lead. Okay, so to conclude, we suggest that sphere hindcast can provide skillful predictions of wintertime North Pacific blocking frequency due to atmospheric predictability sources and tropical SSTs associated with ENSO, particularly when there is no lead time. And sphere hindcast with lead months rapidly lose prediction skill for North Pacific blocking, partly due to its strong modal drift to atmospheric mean state to its climatology, such as Z or storm tracks, which are crucial for representing the variability in blocking frequency. And finally, we propose a hybrid statistical dynamical model based on the ENSO blocking linkage as a potential means to enhance seasonal prediction skills for the North Pacific blocking, potentially extending up to lead times of 7 months. Well, with that, thank you for your listening, and I'll answer to the questions in the later discussion.
So we'll move on to the last talk of this session. That's Jacob Maddison talking about trends in Greenland blocking.
Yeah, thanks, Isla. Hi, everyone. I'm Jacob from Exeter in the UK. So I'm going to present the work I've been doing during a postdoc looking at blocking over Greenland in summer with a focus on a new recent trend that was identified in observations that is missing in models. So this is a nice photo of Greenland. It's hard, at least for me, to kind of comprehend how much ice there actually is over Greenland. At its thickest, it's more than 3 kilometers deep, which is higher than the mountains we see out front, and it constitutes 3 million cubic kilometers of ice, which we're melting. So I'll present a quick introduction and motivate the project, why we're interested in blocking over Greenland, and then I'll introduce this apparent increasing trend in observations that is missing in models. I'll briefly summarize how well the models represent Greenland blocking, and then move on to my results, which is kind of a straightforward assessment of models, how well they represent blocking over Greenland, and then show why we think there's two potential drivers of the variability of Greenland blocking, and then finish with some conclusions. So this slide is just summarizing what's happening over Greenland in the summer. So as you all know, temperatures are rising, and over the Arctic region, they're rising rapidly. So you can see on the left panel from around 1990, a strong increase in surface temperatures. This is causing the ice sheet over Greenland to melt. So since the year 2002, around 270 billion tons of meltwater have been released into the ocean, which then contributes to sea level rise, with about 15% of the total sea level rise coming from the Greenland ice sheet. So the one process that's been shown to be key for summertime temperatures over Greenland is blocking. So we want to understand blocking, and we want to have models that can represent blocking well, so we can get these kind of impacts right, which then feed back onto like global climate circulation. So that's why this top left plot was kind of concerning when it first came out. So this plot is showing, as a function of year, Greenland blocking index, so just how strong blocking is over Greenland. The colors are a bit faded, but you can see, I hope, CMIP 5 and CMIP 6 ensemble members in the light colors. The dark colors stand out. They are the reanalysis products, which show a strong increasing trend in Greenland blocking around 2000. That is well outside the spread of the climate models. And this is not just present in reanalyses, we also find in observations. So the bottom panel shows an NAO index based on pressure observations. And we can see towards the end of the time series, again, a sharp decrease in the NAO, which reflects a strong increase in Greenland blocking. So as I mentioned, we're interested in this because it has large effects on the ice sheet, which is kind of summarized in the right-hand panel. So this is composite of anomalies during blocked versus non-blocked periods. So the top row shows higher geopotential heights, as we expect, higher surface temperatures of more than 4 degrees, which then causes, in the bottom panels, focus on the right-hand side, you can see increased melting and reduction in the surface height of the ice sheet. So as Reinhard mentioned, there's been lots of studies looking at blocking models and what might be missing. This is just a summary slide of biases in summer for blocking. So there's been 2 recent review papers about blocking in the literature, showing in the top panel frequency biases for different generations of climate models, and in the bottom for different blocking indices. Because we've heard a lot already this week that blocking indices can make a big difference into kind of the results we find. But there's a consensus that models underrepresent the amount of blocking we get. And the right-hand side shows what the models project for the future, which is a general decrease in blocking for much of the Northern Hemisphere, potentially less over the poles. But if you aggregate that over Greenland, you see that the observations lie a strongly positive trend over Greenland, whereas all the generational climate models show a decrease. So there's something going on here that the models can't capture this summertime Greenland blocking. So maybe a process is missing, or just there's been some recent variability in blocking that's highly unusual. So my work has been kind of looking at how models represent this summertime variability in blocking, kind of focus on the decadal scales. So this is under review currently at GRL. Hopefully we'll get the reviews back soon. So to summarize what we've done, we've looked at a large ensemble of climate models. So from fully coupled simulations Really coupled simulations as well as atmosphere only, and then single forcing experiments, so where the model's running just one forcing, so aerosols or greenhouse gases or natural forcings, and then some of the high-res MIP simulations as well. And then we identify blocking in 4 ways. Don't have time to go into details, but they're all based on Z500, as this is commonly output from climate models. If you want more details, I'm happy to answer about the indices. So then the first result, this plot is again showing time series of blocking over Greenland in 4 different indices, in era 5 in black and the coupled models in blue. This is kind of an extension of that plot I showed a few slides earlier, including more models and more years. So one thing that's clear, this increasing trend hasn't continued. So Greenland blocking is not just going to run away positively into the future. We have seen a return to more climatological values. But nevertheless, we can see that era 5 remains a clear outlier compared to the climate models. They don't simulate an anomaly of blocking as strong as that seen. The orange shows the ensemble mean, which shows very little signal, but I'll come back to that later. That was a couple of models. What about if we include the single forcing and AMIP and high-res MIP models? Do we see any difference? The short answer is no. Era 5 remains an outlier in each of the model experiments. Potentially, there are some models in the AMIP runs where there's some models that look like they're doing the same thing as Era 5, but don't think it's the actual maximum. If we think this trend is a forced response, we would want the models to be showing some signal at the right time. Whereas if we think it's just kind of variability in the system, models might have such an increasing trend in Greenland blocking at some point in their evolution. So that's what we wanted to first test. So to do that, I kind of quantify this trend, this increasing trend in Greenland in 2 ways. So first, we look at this green line, which is like a 10-year trend in Greenland blocking. So I compare that trend in era 5 to all the trends in all the members in all their time periods. And then we compare kind of this triangle, the average anomaly of blocking during that increased period. We look at the average anomaly as well as the length that the Greenland blocking stayed above a certain threshold. That is summarized in this figure. So on the left, I'm looking at distributions of these 10-year trends in the models. So gray shows era 5 distribution of trends. We see it's approximately normally distributed with an additional peak of around 1, which is this strongly increasing trend we see in the recent period. Whereas in the models, none of them really get a trend as strong as this, kind of as we expected. And era 5 remains a clear outlier. So the models really don't ever simulate such a strongly increasing period of Greenland blocking. Then the right-hand panels quantify this triangle shape. So the top panel shows the fraction of models that have a period of blocking that is this strong as a function of smoothing. So I should have mentioned the time series I'm showing have been smoothed at a rolling window of 10 years. So I've now compared for different smoothing lengths, but it's not very sensitive to that. So the models really do, well, less than normally 1 in 50 of the models get a period of blocking this strong. More of the models can simulate a period of blocking that's that positive, but it's not as strong. So it seems that this trend really is, the models aren't capable of representing a trend like this. So potentially there's some missing component of blocking that we need to better understand. So going back to this plot, now I've added in the panels the correlations between the ensemble means and the observations. So if we average the ensemble members, we kind of remove internal variability and we're left with the force response. So if this correlates strongly with the observations, we think there might be some driver of blocking based on that. So we can see that in AMIP and the aerosol experiments, the time series correlates very strongly with observations, suggesting there's some force response potentially from the atmosphere or sea ice, from the ocean or sea ice, and or from aerosols that potentially are important for blocking. So you can correct this. So it's quite well known that models do contain predictable signals both on seasonal and kind of decadal timescales. but this signal might be too weak in the models. So you can correct the ensemble mean using this equation, which basically corrects, so the ensemble mean has the same variance as the observations. So we only do this for experiments where we think there's some predictable signal. So that's where there's a strong correlation, essentially. So if I now plot in the dashed orange line the corrected ensemble mean, we can see that for at least AMIP and the aerosol, that now the time series somewhat resembles the true time series. So this kind of indicates that there potentially is some forcing from, as I say, either the sea ice or the SSTs or the aerosols, but the models don't respond strongly enough to this forcing. So at this point, we don't know if potentially the sea ice SST forcing and the aerosol forcing is coming through the same kind of mechanism, where the aerosol is influencing the SSTs, and then both experiments get some force response. So this is just showing that we shouldn't be too surprised that the SSTs and aerosols potentially influence blocking. There's quite a lot of literature out that blocking is sensitive to SST patterns as well as aerosols. So this is a previous study looking at different configurations of models where we see that there's a strong increase in trend blocking over Greenland in the observations, not much in the models, but there is if you include atmospheric aerosols. So we wanted to see if these two potentially different mechanisms were working through the same pathway. So we try and quantify that here. So the top panels show temporal correlations between SSTs in the AMIP and aerosol experiments. So we think if the aerosol experiments were modifying the SSTs, they'd have similar kind of time evolution as that in the AMIP, because AMIP follow the observed time series. But we find that correlations are very low, negative or weakly positive. So we don't think that aerosols are having the same impact as the SSTs. This is kind of further evidenced by looking at the SST anomalies during that strong Greenland blocking period. So I'm looking at the anomalies of SST during kind of the period when the blocking increased, on the left for AMIP and on the right for the aerosols. And in AMIP, there's kind of a signal you'd expect, kind of warmer SSTs around the surface of Greenland, around the south of Greenland, whereas in the aerosol experiment, there's no signal. So all the models are doing different things with their sea surface temperatures, whereas in AMIP, they're obviously all doing the same. So we think that these are acting through different pathways, but we still don't know which one's the dominant driver, because the AMIP experiments also include the aerosol forcing, so it's not a perfect comparison. But to conclude, then, we think that recent period of increased blocking is not a sustained trend and it has stopped. It could potentially start increasing again. But such a period of blocking is very rare still in climate models, suggesting 2-week response to forcing or some missing processes in the models. We did find that the multi-model mean of the atmosphere only and aerosol experiments correlate strongly with the observation, suggesting some force response that may be too weak in the models, but they don't seem to be influencing Greenland blocking in the same way. So I'm currently then running experiments with the Met Office model where I run it in AMIP mode without aerosols to see if we lose this kind of response in the AMIP simulations, which then suggests it's the aerosols that are the driving force. If it remains, it could, still be the SSTs. I'll stop there. Thank you.
Thanks to all the speakers for some great talks. I just want to invite all the speakers to come and sit up here for the discussion. And a reminder to the online participants, please raise your hand, and then Alyssa will either unmute you or ask your question. So let's start in the room. Any questions? Yep, please come up to the mic.
Waiting for.
Oh.
Very good. Thank you, everyone. Some really great talks. I just a couple of quick comments. The first quick comment is about the seasonal forecasts. It might be worth considering if you're going to look at the seasonal forecasts to get rid of the first 2 weeks and then look out further, because it's almost certainly the case that you're front loading all of your skill in the first week. And that if you go beyond that, that's a better metric. For the seasonal models, right? Yeah, and the sub-seasonal models. Reinhard, you brought up some really excellent points regarding the SST stuff, and I just had a comment about that, which is that I think I would maybe encourage the community to dig into the sub-seasonal, seasonal forecast models. I know they're more of a pain to deal with than the CMIP models, but I think that a lot of the biases and things that you get when you look at the CMIP runs is convolving a bunch of stuff that you're getting some sort of long-term error, but that's not really maybe the error. And I give you an example that you brought up that I think one of your conclusions is probably very much right about, which is that if you look at the seasonal models and you look at the errors, you see these SST biases. If you look from the initialization time moving forward, those SST biases show up in like 2 weeks. And the implication there, I think, is that that's probably way too quick for the SSTs to have established that bias. And probably what's going on is the atmosphere has a big bias and there's a wind stress on the ocean, and that's starting the bias that then, feeds back, and you have this big SST jet blocking bias. But that if you're really going to try to solve the problem, you need to look where not at the steady state, way out, you need to look at where it emerged from. And I think your conclusion that a lot of that is intrinsic to the atmosphere is probably right, but that might be the better way to start looking at these things is in the initialized forecast models. Does that make sense? Or do you have comments or pushback on that maybe?
I think it sounds entirely consistent to that Davini study that I showed, looking both at the free running climate models using the IFS model and their seasonal prediction model. The seasonal predictions with the same model. And so from that paper, I take it that compared to the free running models, the SST biases across the forecast period, I think it's November, and then looking at the next winter, they're much smaller compared to the SST biases you get in the free running climate model. So that's a way of disentangling that. So you can say, okay, here I have a modeling system that has ARC interaction, but doesn't have the SST biases that the free running models suffer from. So I think that sounds entirely consistent. Also, having such seasonal forecasting systems with the same model, it's extremely valuable, I think.
I guess that was the larger point, was that that dealing with all these biases probably best maybe dealt with in that context. Forecast systems as opposed to.
Yeah, I'd say using a range is it's important. Yeah.
Mingyu, did you want to respond to the first part?
No, I think totally agree with it.
Okay. All right, we'll go over to this mic and then back to this one.
I have a question to Mingyu. Very interesting study. In your hybrid model, you have two predictors. I was wondering if you examined the relative contribution of the two predictors. If the model has difficulty predicting blocking beyond 1 month, I would expect or suspect that the model cannot capture the upstream precipitation either. So my suspicion is that most prediction skill comes from the NINO 3.4 index.
Yeah, you're right. So most skill comes from the NINO 3.4 index, and the upstream precipitation works as a secondary predictor, but it still gives a substantial, I'll say, a significant skill for the first several months. So we thought it's useful to incorporate the predictor in our hybrid model. Yeah, and the source of predictability source of upstream precipitation is also from the local exotropical SST, independent of the NINO 3.4 index. So I think that kind of justifies our usage of upstream precipitation as a predictor.
Okay, thank you.
Yep, thanks.
My question is for Juan, and I'm Ken. I'm also I'm a math major undergrad at New York University. Yeah, first of all, great work. I've seen at presenting partial of this work in the group meetings. But my question was on the transfer learning part, that I read a very interesting paper by Pedrum's group. I think Pedrum's also here. The first author is Adam, who's also in Quran right now, about the retraining of the transfer learning in the convolutional neural networks. And I know it's a common approach that for the computer science community to retrain the last or the deepest layer that you've also did in your work. But I think for that paper, there was like more of the to be more physically consistent, is that actually you retrain the shallowest layer for the neural network. I'm wondering if you're aware of that work, and I'd be very interested to see if the work has been, the transfer learning has been done on the first layer.
So can you hear me? Yeah. So first, thank you for your question. And I indeed read that work before. And actually, I started from training the first layer, and then it was not really great. And then after making efforts for a long time, I decided to train other layers. And then I found the last layer is the best one. And I guess this conclusion, I mean, is actually very interesting. And I think that's very specific for different systems, and sometimes you need to emphasize large scale stuff, and sometimes you need to learn small scale features. And here maybe I think sort of understandable, because Error 5 and because the Marshall-Martini can only capture the large scale, like deformation scale, but Error 5 actually depends on lots of small scale instabilities. So it could be that the deepest layer, which characterizes the subtle, differences, could make a lot of difference. That's my question. That's my answer.
Thank you very much.
We're going to go to an online question.
Yes, we have a question from Ping.
Yes, hi, my name is Ping Liu from Stony Brook University in New York. I have one comment and one question. The comment goes to Dr. Mi about the sphere biases. We diagnosed the GFDO models recently, including the SIMF4, about the blocking simulations in SIMF5 and SIMF6, and we found similar biases as well. Excuse me. Well, we also found that if we substitute, replace the climatology in the model with the climatology observations, the overestimate could be reduced substantially. But I saw that your the index for blocking was about the anomalies. So I'm wondering whether to remove the zonal mean in your diagnostic would impact or would reduce the biases. That would be my comment. And a question about the Greenland blocking goes to Dr. Schiemann. Did I say that correctly? I'm sorry. I saw your composite in your slide number 11. The composite about the Greenland blocking composite. I didn't see well any reversal by definition in that area during those composites. So I'm wondering whether the composite include Greenland blockings blocked in different longitudes, such that the final composite would smooth away those reversal signals. So I'm wondering whether more specific composites would make the reversal of the flows stand out, such as the first longitude blocked events is composite, then the next longitude blocked events are composite, like that. That would be my question. Thank you.
Thank you. So it is actually the composite with respect to that single grid box, and when the reversal index picks up at that grid box. Other than that, we probably need to follow up on that offline. I don't have a quick answer. So you do see the anticyclonic Rossby wave breaking in the composite.
Okay, I'll check that later. Thank you.
Oh, can I also answer to the comment? Thanks for sharing the comment. And we actually applied the mean bias correction for the seasonal hindcast, and it indeed reduced the mean climatological bias of blocking frequency. So yeah, we already did that. Thanks for the comment.
Thank you. Yeah.
thanks to all of you for the really interesting talks today. In my mind, I really like the dichotomy of looking at sort of the biases between the climate models, but then also the forecast perspective. And it got me thinking from a forecast perspective, you have the ability of knowing what the verification is. And so in the model, you can say, we're forecasting a block, it doesn't happen. Why is that in terms of what actually happened? You have that sense to say, oh, well, like it formed a block in the model, but it's too far east compared to verification, or maybe the flow didn't get as highly amplified. But in a climate model, it's a lot more difficult to know what actually verifies to sort of determine maybe kind of, are you getting close to a blocking situation in many cases, but just maybe not getting over the threshold of it to be identified? And I guess my question is more of a sort of a thought question from the standpoint, do we know within climate models whether, let's say, we have these situations where synoptically you're getting close to producing a block, but maybe not quite getting over sort of that threshold value? Or is it a situation where we're just not even reproducing situations that could conceivably evolve into a block at all? I imagine if it's, you know, a phase difference of the climate model's producing a block, but it's too far east, it's still at least showing up in the statistics as a block locally, where regionally you might have that representation. But I guess, do any of you have any thoughts on sort of the representation of sort of that close but not quite scenarios synoptically within the climate models, where it's sort of on its way to maybe producing a block, but just isn't quite getting there?
Perhaps a partial answer. So I haven't looked at that exactly, that problem you're describing. What I and several other people have done is a pragmatic approach to this whole question of blocking identification, which is a long discussion, is to take more than one index. And so, for example, the results I showed there. So I showed the results for a reversal index. If you do the same with an anomaly index, you get qualitatively the same. So these statements, like comparing the CMIP5 and CMIP6 performance, they are robust in that sense. But of course, some of these indices, for example, the reversal one, or most of them, they have some absolute thresholds in them. I think many were developed for the Atlantic winter case. So I think it could be interesting to check the sensitivity to that. I haven't done it personally.
I mean, I just like to add, I think, as you said, we can't really compare block by block in climate models. So you have to like look at the statistics kind of more and see if you get kind of average of the block characteristics right. But in terms of, I don't know if it's more that they don't quite get the block. I think they just don't. You do see like realistic developments of blocks in climate models that look like they could be real blocks. So I think it's just more as they lack the initiation of at a certain point that then never comes into a block, rather than nearly getting there. That'll be my hunch. But
thanks so much.
Yeah.
And my question is for Huan Zhang. So first of all, very interesting work. And I have two very short questions. First, let's suppose you have a million days of meteorological data from state-of-art models. If you train that, would you expect better scale?
Can you repeat your question again? Sorry. What did that?
Neural network model on the data from state-of-art models.
Oh, yes, yes.
Scale.
That's actually the next direction, because we wanted to. I think the next step is to start from handcast S2S data. So that's better. And for this idealized model, I think at first we wanted to study more about this idealized model. So so one of our goal is to compare really the difference between the prediction of this idealized model and real data, so we can study it better. So it's more of science significance.
The marshall motility model is a dry model, right?
Mm-hmm.
So
it's dry, right?
Diabatic processes, so it probably missed a lot of
indeed, yes,
the driving factors from diabatic processes. So another question, probably interpret around like you have a kind of a fine tuning module.
Yeah.
For the transfer learning part.
Mm-hmm.
And can I interpret as kind of a bias correction?
Yes, that's I think it's correct. It's bias correction, and you can notice that we freeze the first several layers and only change the last one. That's actually has two someone has asked me before whether this will keep some bias because you freeze some of the parameters, but this is like a bias variance trade-off, right? If you retrain every parameter, then you will be likely to go back to the direct training, which has lots of variances. And in order to keep the previous advantage gained from the robust pre-training, we fix lots of parameters to avoid the overfitting that could be possibly obtained. Yeah. Thank you.
Oh, yeah.
Hi. So I have two questions, one for Reinhard and one for Jacob. So for Reinhard, I guess I was wondering how robust do you think your projection for the decrease in blocking frequency is, given that you used one index? I was wondering if you looked at more indices, and just because I thought there was a disagreement sort of in the literature about whether it's decreasing or not, so I'm very curious about it. And then maybe I'll also say my other question for Jacob. I was wondering if such a strong trend in Greenland blocking should probably also manifest in, other variables like the location of the jet, the storm track, so many other things, right? It's so important for mid-latitude circulation. So I was just wondering if you looked at other variables, do we see this similar discrepancy between R5 and models?
Thanks, Talia. I actually haven't looked at the projections myself. So that particular study I showed, it's also based on a reversal index, I think. And first of all, yes, the models, they agree. The models agree a lot. Second thing I can say is, if you go the other way, if you take these indices, and that's what I tried to do very briefly with this composite, if you interrogate these indices and look at the cases they identify, you find blocks. So in that way around, they work. But similar to the discussion we just had, there may be cases they miss. And for that, I don't have a very good answer to you. So yeah, I think, yeah, there's more work to do on the robustness of the projections. In a way, what I did in a way is the simplest problem, maybe. Because for the model evaluation, we always take one or two indices, so we try to take more than one, and then we do the exact same thing in the reanalysis and in the models. And then even if the indices are not quite perfect, if we get a bias, that's not good, right? But once you start thinking about trends or decayed variability or the projection trends, it actually gets probably a bit trickier. Yeah.
And yeah, I think that's a really good point. So we found that in Era 5, the blocking in Greenland is very strongly negatively correlated with the jet latitude, as you'd expect. But in the models, it ranges from positively correlated to quite strongly negatively correlated. So we think there's some sort of disconnect in the models between blocking in Greenland and can kind of operate on its own without influencing the jet stream so much. We don't know why that is or how that would happen, but that's what we found so far. Yeah, but it's a good point.
Questions for Dr. Jacob. So with this Greenland blocking stuff, in your opinion, how influential do you think the sea ice is compared to the other things? And if you think it's really important, then do you think the discrepancy could be related to maybe some of the diabatic effects when you have the ice melting? And then also, do you have any plans to do any sea ice experiments?
So yeah, I do think the sea ice is one factor that's influencing it. There's quite a lot of work that's shown that that has a big impact on the circulation in the region. I don't think we're going to do any experiments looking purely at sea ice. It's more boundary conditions, so sea ice and SSTs versus aerosols. I'm not a sea ice expert really, so yeah, that's my answer.
Thanks.
Pedram?
Yes, I want to clarify something about this issue of deepest layer versus the shallowest layer. So I think a big difference between what you do and what we did is that you are doing classification and we did regression. And so when you do classification, like what machine learning people usually do, the deepest layer, that's where you learn a lot of the stuff about the system. And so that's why the last layer would be still the best to to retrain. And in regression, it's very different. So that's was the point in the paper. But also I have two questions about the explainability part, which I thought was really nice. One is, have you made this map of these SHAP values for different lead times? If you do that, basically, do you see a wave train? Is the CNN learning from a wave train? The other thing is, have you looked at the SHAP values for cases when there is wave breaking, but you don't get blocking? Like, can you see what the CNN, how it learns that this wave breaking would not become a block?
That is a very good question. I'm thinking whether we have done that before.
That's okay, just a suggestion.
Yeah, I guess we didn't really do that. We only plot the SHAP values for the correct predictions. Yeah, but we didn't really, moreover, we only predict the true positive composites. So positive usually means this is actually a blocking event, but it's actually pretty, oh yeah, I remember we once make the composite of true negative events. And true negative events are sort of pretty much the same as true positive ones. And so finally we decided to show the true positive ones. But it's a good suggestion to go back and take a look and do some further analysis.
Yeah, very nice talk, everyone. A question for Reinhard. So the high res models, I guess they're kind of a bit experimental and they're obviously very expensive. Do you think that kind of with more time and money spent to tune those models, they could get us even closer to the observations?
So I don't have a full answer, but maybe some comments on that range of issues. So at those sorts of resolutions going to 25 kilometer, we've seen that especially the ocean resolution seems to matter quite a lot because it helps with some of the SST biases in the models. But then once that is sort of fixed, we are still not there. So that's the example I showed for Central Europe. And because we don't have sizable SST biases left, it must be something else. And from that example from the Diabatic study, it would really be issues in the atmosphere model itself. I think what is very valuable in general is to have as seamless systems as possible so that we can learn across the range. Because at least it gives us something to do, or if we get results from the medium range scale, we can check in the climate model. So we can go across and so that is, I mean, you can't have it overnight, but having many, let's say, modeling systems that cover the whole range. So where you have medium range, where you get seasonal, decadal, where you have PPEs, and the free running climate trends. I think that gives us at least a lot of options to study blocking biases. In terms of your question about if further resolution increases may resolve these issues, perhaps. I mean, in the atmosphere, we know that diabatic processes are incredibly important, and the community is now going to kilometer scale simulations. It'll probably be a while until we have good blocking statistics, but yes, it's trying.
I guess I'm just wondering about model tuning, right? The low resolution models have been kind of tuned, carefully tuned over many years. And I wonder if once the high res models go through that process, whether they'll be even better. Yeah, I don't know. I'm kind of skeptical, but it could happen, I guess.
So I'm not entirely sure. I don't think tuning is the main issue for that generation of models at the higher end of the high res models. They are reasonable climate models in that sense. They don't terribly drift. Yeah, I don't have a full answer. But yeah.
You go first.
I have a question for Jacob. Are you aware about the study that showed the impact of the IMV on the NAO? Because your study is pretty consistent with this, and we have tendency when you have one IMV to have negative NAO, and therefore to enhance the Greenland blocking. You look on the summer or on winter?
Summer.
Summer. No, this result was also only on the winter, sorry. But there is also indication that we have some multi-decadal variability in the summer NRO.
From the AMV, so.
I mean, there is no study on that. Only on winter. Sorry, I was. Thanks.
Hi, this is Seraphine Hauser. More a general question to like everyone on the planet, but also in the room. Something that kind of came up also during the breakout sessions yesterday. So one thing we talked about when we think about blocking identification, we think of persistence. So I was in general wondering, is the underestimation that we see in blocking frequency, is the problem more that the block is like that the models kind of miss the onset of the block? Or is it more related to, okay, we see that there's something developing, but it's like too short in persistence to be identified as a block? And as a second part also, what role does maybe different flavors of blocking play? Like, do we see like differences in the predictability of blocking types? And if they change, like when we think about long-term in the future, does this impact also like the representation in the models? And does this kind of explain maybe this underestimation?
For the first part, I think Paolo Davini examined separate the bias to persistent bias and onset bias in the seasonal hindcast. I think what they found is onset bias is a main driver of the bias in general. Persistent bias, of course, important, but not as important as onset variability bias. Yeah.
I think that's the same for weather forecast models as well. It's that the onset is what they really struggle to pick up kind of at 5-6 days lead time. The ones that blocks in the forecast, they're quite good at keeping it there.
So I showed these plots showing the aggregate root mean square error. So and then you can also look at other metrics like just mean blocking frequency or persistence. And when you do that, it's really a mix. So persistence is important, again, from memory, especially for the Atlantic winter case. But there's also too little blocking in the models just in terms of frequency. And it is very model dependent, especially this persistence issue.
I want to make some additional comments on the data-driven approach. Well, usually the problem for long time lasting blocking events prediction is usually that we have too little data to train a neural network. Yes, and also even if we have trained a neural network robustly, it's hard to make a large enough test data set to test its ability to predict. So I think this is a question that we always want to suffer and always want to develop, and transfer learning is one of our efforts. And for direct training, I don't know what other thing we do if we only have observational data.
Yeah, just a very quick question to Mingyu. So, like in a seasonal prediction, have you you use two predictors, ENSO and upstream precipitation? I was just wondering, like, have you tried other predictors as well, or in your opinion, what would be used as a predictor that could maybe give us a better lead time as well? So, thanks.
Thanks for a good question. So I haven't tried other predictors in this hybrid model. I think CIs, as we mentioned, can be a good variable to test, but I haven't tested.
Oh,
Quick question.
Sorry, did someone else want to chime in?
Have you?
Yeah, go for it. Sorry.
Just very briefly, I think there was a second part to Seraphine's question about broadly about the blocking flavors. And in the climate model runs, we've done a lot just applying these straightforward indices because it's simple to do and you have lots of data to apply it on. But I think we can learn a lot from the initialized work, looking, for example, at wave breaking types and yeah, just being a bit better than just applying one index. And also, I think that's more interesting than trying to find the best index. It's more completing the picture with different dynamically meaningful metrics. Also, that study that I showed led by Oscar Martinez, looking at the tropopause gradients of PV, things like that.
Please.
Have you considered that, this could be for anybody, on the western side of the block during ridge building, particularly during the warmer part of the year, if you're not getting the precipitation right associated on the upstream conditions, then you're not producing enough negative potential vorticity advection by the rotational wind, which is a very big factor in ridge building downstream. So how well are the climate models handling that aspect of things in terms of both precipitation intensity, duration, and then the resulting negative PV advection by the rotational wind?
I mean, yeah, that's a good point. I think one thing it's hard to calculate lots of PV diagnostics in the climate models because they A, don't output, and B, they're quite low resolution. So like the gradients of PV we need to kind of assess aren't there kind of by definition. But I think it's more result. You can look at the kind of parameterized processes. I think it's still quite lacking in the climate models. They don't get kind of enough latent heat release and, as you say, PV negative PV tendencies in the upper levels. But yeah, it's important to look into.
Yeah, but that's the kind of thing the weather guys are going to look at because that's very critical to block building.
Yeah, definitely, yeah.
Hello, everyone. As people are joining, we will be starting our second round of lightning talks. Our first speaker here is a video, so we'll get that started here in a couple seconds.
Hey everyone, my name is meteorologist Sarah Weaver, and I am a PhD candidate from the University of Missouri, located in Columbia, Missouri. Today I want to talk to you about atmospheric blocking and drought patterns, an in-depth analysis and comparison of the dry summer of 2022 in the Midwest USA. Before I begin, I do want to say if you'd like to check out our work, we just had it published. You can scan that QR code and it'll take you directly to it. So imagine a world where we can predict droughts months in advance, giving communities the time that they need in order to prepare and minimize the impact on their lives and economies. That is what the vision was that drove our latest research. We've been exploring things such as atmospheric blocking and its profound impact on weather patterns, particularly its correlation with drought conditions in the Midwest USA during the critical summer months of both 2022 and 2023. Atmospheric blocking involves high-pressure systems that linger over a region for an extended period of time, which disrupts normal weather patterns. Our findings have shown a direct link between these blocking events and the onset of severe drought conditions. By analyzing data on the 500 millibar geopotential height anomalies and integrated instrophy, we've identified patterns that not only explain the dry and hot conditions during these summers, but also offer potential predictive tools for future drought forecasting. The significance of our work lies in its potential to transform how we predict and prepare for droughts. Current forecasting models often struggle with the long-term prediction of extreme weather events. Our research introduces a method that could significantly enhance the accuracy of these forecasts, providing a valuable tool not only for agricultural planning, but also for water resource management and climate strategies. However, our understanding of atmospheric blockings and its interactions with global climate patterns still remains incomplete. To fully unlock the potential of this research, we need further studies that delve into the mechanisms behind atmospheric blocking events and their evolving nature in the context of a changing climate. Understanding how global warming might alter the frequency, intensity, and impacts of blocking events could be crucial for improving our predictive capabilities and preparing for future climate scenarios. In conclusion, our research opens the door to a new era of weather forecasting, where advanced warning of drought conditions can lead to better prepared communities. The next step is to broaden our investigation, where we explore the intricate dance between atmospheric blocking, global climate patterns, and extreme weather events. Together, we can pave the way for a future where the devastating impacts of drought are significantly reduced, safeguarding our environment, economies, and communities against the unpredictable whims of nature.
IS 2.0 to identify the warm conveyor inflow and the warm conveyor flow and the relationship to the atmospheric blocking biases. In the second part, so the blue rectangle, we present some results from the storm resolved models, and they are high resolution climate models, and we evaluate different properties. In this case, I show you the intensity, and you can observe, maybe it's difficult from this figure, But if you go to the poster, you will realize like as the resolution increase, the intensity of the blocks it's closer to the reference that is the era 5. So, and also it's observed these improvements at extremes. So if you are interested, please look at the poster. Thank you.
Thank you so much. Our next presenter is Christian Grams.
Hello, everybody. Yeah, my name is Christian Grams from Meteor Swiss, and I'm presenting today two case studies, basically, where we investigated at KIT and together with colleagues at ECMWF how synoptic weather activity and the interaction with the extratropical waveguide basically affected predictability of recent extreme events. And the extreme events related to blocking that we looked at are the Pacific Northwest heat wave, of which we have heard already in this workshop. So on the right, you see a depiction of that, of the temperature anomaly and the PV anomaly related to that. That extreme event. And then another recent one, which Reinhard Schiemann also mentioned, was the 2023 September Omega block over Europe with flash floods over Iberia, upstream and downstream with heavy large-scale precipitation over Greece and the deadly floods in Libya. So next, please. So you see there were different extreme events related to that recently. So a record high 0-degree line. Could you go? Well, anyway, you see the poster. So no, just go to the next slide. It's almost over. So what we see in terms of predictability, so this shows the forecast with different lead times, the forecast for the heat wave on 29th of June. To the right, on the left plot to the right, you see the model climate and you see the red line that the actual temperature was out of the range of model climate. And you also see that forecasts at different lead times, they only suddenly, roughly a week ahead, they got the magnitude right of the heat wave. So you have this step in terms of predictability, and we call that a predictability barrier. And likewise for the precipitation here exemplified over Greece, you see that step only a couple of days before the extreme event. You see a step in the ensemble distribution of the forecast going towards the extreme, and then also the observed case. And for both cases, we can link, if you click once more, we can link this predictability barrier to synoptic activity. I'm not sure yet the animation appears, related to warm conveyor belt activity far upstream. In the case of the Pacific Northwest heat wave, it was an unusual Mayo-Bayou-front precipitation in the West Pacific, and then downstream Rossby wave development and amplification. In the case of the European blocking, it was extratropical transition of two tropical cyclones and a complicated flow interaction that built up the ridge. If you're interested more, you see a Zoom link where we can also chat live, and I post the Zoom ID also in the chat later. Thank you.
Our next presenter is Lin Liu.
Yeah, thank you for giving me the chance to present this virtually. And well, today I'm going to present about the Greenland summer blocking characteristic and evaluation of high resolution multimodal ensemble. So this is a complement work to the work presented by Jacob Maddison earlier today. And we focus on how high-res MIP model reproduce spatial patterns of summer Greenland blocking. So we use two indices in this study to define blocking events. One is the GB2 Greenland blocking index, which is a normalized Greenland blocking based on geopotential height at 500 hectopascal. And the second one is the flow reversal index by Davini et al. 2012, which is basically mentioned by other presenter today, earlier today. So the idea is we use two indices and define all the blocking events in the summer from either era 5 or model simulations, and we just pull all the blocking days together. And then here, looking at the plot, you see this is the bias between each model in the high-res MIP compared to the era 5, with the shading colors presenting the bias, and we the contour lines, the green solid contour is the model, and the black dashed line is from era 5. So basically, we can see that those model in high-res MIP ensemble can reproduce the spatial pattern, which is with the omega shape over Greenland. But there are some systematic bias, and looking at, for example, a few models like CMCC or MPI, which those are the red model all over the domain there, we see there is not much clear difference between a higher resolution and lower resolution of those models. And could you please move to the next slide? Yes, and the second part, we use a supervised machine learning technique called self-organizing map with a structure of 3 rows by 4 columns to cluster all of the blocking days in the summer from era 5 into 12 different patterns. And if you look at the left panel, we see that, for example, the first, the second, the third, the fifth, and the sixth panels, they show the omega blocking patterns from era 5 reanalysis, and the panel number 9 to 11, they are the cyclonic wave breaking structure with a very clear cutoff flow to the south of Greenland, and the high pressure system retrograde from the Scandinavia toward the Greenland, and the rest we are the Atlantic ridge. So this is the result from era 5, and we apply similar procedure to all models in the high-res MIP, and then we group those 12 main patterns together and take the means to receive the final result of the 3 patterns on the right-hand side. If you look at the upper part of the right-hand panel, they are 3 different patterns from era 5, and the bottom part, which is the model, multi-model mean minus era 5, and we can still see similar pattern like previously in previous slide. The model can reproduce spatial pattern of the 3 different main patterns of blocking over the Greenland, but there are very clear systematic bias. So the take-home message here is like high-res MIP models can reproduce spatial patterns of Greenland blocking with systematic biases, and higher resolution models do not show significant improvement in representation of blocking. So thank you for your attention.
Our next presentation is recorded, and it's by Matt Miller.
Aloha, mai kako. My name is Matt Miller, and I'm a PhD student working under Dr. Giuseppe Torri at the University of Hawaii at Manoa. Today, I'd like to focus on a particular type of extreme weather pattern known as a cutoff flow. Cutoff flows are cold cord, low pressure circulations that develop in the mid to upper troposphere after detaching from the polar jet, hence the cutoff in their name. Associated with omega blocking patterns, these systems often originate at the mid-latitudes and then subsequently drift equatorward. Over the years, cutoff flows have attracted much attention because of their potential to bring severe flooding to many subtropical regions. In Hawaii, for example, these cutoff flows are called Kona lows, because the term Kona refers to the anomalous southerly winds that these storms bring to the islands. These storms can trigger heavy rainfall, flooding, and mudslides that cause major infrastructure damage, like the Kona low in early December of 2021. For this research, we are using an aquaplanet model to investigate the dynamics of cutoff flows and answer 2 interrelated questions. First, we want to understand how future warming conditions may affect the physical characteristics, locations, and durations of cutoff flows. And second, we want to understand the mechanisms behind cutoff flow formation and the sources that cutoff flows derive their energy from. We first constructed a detection and tracking algorithm that uses 3 filters at the 250 HPA pressure level to search for cutoff flows. The first filter searches the geopotential surface for any local minimums in both the lat and long directions, so essentially any areas that could hold water if we were to pour some over top. The second filter checks that this local minimum is at least 50 geopotential meters below the longitudinal mean, and the third filter applies a 4-point cyclonic wind check. We then applied this tracking algorithm to 3 CSM 2.1 aquaplanet model runs. The first experiment is the control run, where we ran the model with out-of-the-box settings. In the second experiment, we doubled the CO2 concentration to 734 parts per million. In the third experiment, we imposed our own sea surface temperature gradient of 27 degrees C at the equator to 20 degrees C at the poles. Each experiment spans about 40 years. Our preliminary composited results show that the 2x CO2 and relaxed SST experiments are markedly different from the control run, which aligns closely with the real-world cutoff flow events. The genesis latitudes in the 2x CO2 experiment have a smaller standard deviation around the mean genesis lat, while in the relaxed SST experiment, we see the distribution is skewed farther north. After more analysis, the next step is to apply a modified eddy kinetic energy budget to ascertain the underlying dynamics for these changes. We'd love to hear your thoughts on the research so far, and any comments, questions, or connections are very welcome. Please feel free to email me at mille285@hawaii.edu to get in touch.
Next, we have Kazuaki Nishi.
I'm Kazuaki Nishi from Mie University, Japan, and our title is Large-Scale Atmospheric Response to Warm SST Anomalies in the North Pacific in the 21-22 winter. And as shown in the right upper panel, there was extremely warm SST anomalies in the North Pacific in this winter, and this was associated with negative PDO. And we evaluated blocking frequency based on the definitions of Tebaldi and Molteni in February of this winter. And the left panel is for JERA55 reanalysis data, and we see a blocking increase over the Western North Pacific compared to climatic mean. Japan suffered from heavy snow by this blocking increase. And we conducted AGCM experiments with two different SST conditions. One is prescribed with observed SST, and the other is with climatological SST only in the North Pacific. As shown in the middle panel, in 50-kilometer AGCM, blocking was increased over the Western North Pacific by the warm SST anomaly in the North Pacific. On the other hand, in the 100-kilometer AGCM, shown in the right panel, we don't see such difference. So our results suggest that blocking response to the warm SST anomaly in the North Pacific may depend on model resolution. That's all. Thank you very much.
Our final poster presentation is from Hong-Yi Lee.
Okay, I'm going to show you about my work with Professor Nobuo Nakamura about how much do diabatic process contribute to the storm tracks. And please do the next slide. This work has basically been used by the local activity budgets, so which measure the wave activity and also identify the wave sources. So if you look at the top left panel, where you have the PV reference frame, which is only symmetric black dash line, and the PV contours, the wave activity basically measures the total displacement of PV from the zonally symmetric PV line to the PV contours. And to trace the wave sources, you basically just calculate total amount of PV transport. So this budget is basically the conservations of PV. And you move on to the bottom left figure. So this is give you the climatology of local wave activity during the winter time from the ERA5 reanalysis data. And you basically seeing the strong wave activity over the Pacific and the Atlantic Oceans, which are representative of the storm track regions. And on the upper right panel is the residual part of the budget. So the residuals basically tells you where PV is not conservative, but still generating the wave activities, especially in the Western Pacific and Northwestern Atlantic, where you have the positive sign with the red shading. And those are likely from the diabatic processes. So next, we perform the local activity budget model. Basically, by just removing those positive residual signals, and then that will make the imbalance of the budget. Then we perform the numerical solutions to figure out the local activity based on this removal of the positive residual terms. And the results is showing in the bottom right panel, the last one, that where the local activity without the diabatic processes was basically decreased by around 20% in the Pacific Atlantic regions. And for the details about this model, you might be interested. Please refer to the virtual poster, and thank you very much.
Well, we have 7 minutes left in our session. So does anyone, either online or in person, have questions for our virtual poster presenters?
Great presentations. I have a question for Hongyi. I think it's great to see that you look into the budget and you show the wave activity when there's no diabatic heating. And I wonder, this is apparently a very close, rigorous budget analysis. I wonder, let's say if you have a dry atmosphere, let's say you don't have moisture at all, would the wave activity be as low as the one that you're demonstrating in the budget analysis, or it's like entirely different world?
Oh, thank you. That's a very good question. I did a calculation directly from the diabatic heating using ERA5 temperature tendency, and their radiative effect and cloud effect and moisture effect, those all contribute to the generation of waves. So if it's a dry atmosphere, basically you might expect it that the decrease of the local activity will be not that much, but maybe about 10%. I didn't quantify it.
Great. Yeah, thank you for your response.
Thank you.
Christian, this is Lance. I have a question for you. You there?
Hi, Lance. Yes.
What role were there any active tropical cyclones in the Western Pacific that may have helped to initiate things in the case you've described?
No, we didn't see tropical cyclones. It was June, so that was early for the season. We saw very strong precipitation along the Mingyu Park, and that had warm conveyor belt-like ascending airstreams and a strong outflow then impinging on the jet. And basically the mechanism in terms of diabatic outflow, negative PV advection by irrotational wind was the same, and it initially built a ridge over the West Pacific region and then the downstream triggering as if there was be a tropical cyclone interacting with the jet.
Yeah, I will figure that was a role in play. Would you say the aerial extent of the negative PV advection by the rotational wind was unusually large? If so, could that have had even more consequences downstream?
I think what we found is that basically the precipitation intensity and also the stationarity was a bit unusual for also for this time of year. And I know that there are other works which speculated about the role of the BSISO mode, so that the early East Asian monsoon that might have affected it and has actually given some predictability on subseasonal timescales because you had a longer phase of blocking, but it is important to know that the subseasonal predictability of generally a blocking situation was good. It was just the magnitude of that particular block where it was a predictability barrier. So there was subseasonal guidance for above normal temperatures, but the extreme magnitude was really only predictable once synoptic dynamics, and in particular then the phasing of other cyclones that developed downstream and the downstream cyclone formed and the warm conveyor belt associated with these downstream cyclones. This phasing issue was was critical for the predictability of the magnitude of the ridge and then the heat dome.
Thanks, Christian. I look forward to reading the paper.
Yeah, thanks.
So I have a question for Matt Miller, but I assume Giuseppe can probably answer that question. This is a blocking workshop, and I think we should be inclusive as possible. Cutoff low is a stationary wave, and in my view, that's part of the family of blocking. So I wonder, how does that actually create extreme events over Hawaii? So because that sounds like a very new thing to me, I want to learn more.
So whenever these cutoff lows come over Hawaii, if they develop a surface circulation, they become subtropical cyclones, and as Matt was saying, they're called conolodes. And for Hawaii, they're actually a pretty significant problem because we usually have 6 or 7 of them every year with some interannual variability. And so there's usually lots of flooding on the islands, lots of losses and deaths. But essentially, yeah, it's just whenever they can develop surface circulations, it just becomes cyclones, and they remain stationary over the islands for a few days. Yeah.
Awesome. I do see a virtual question. So if Pragvala, if you want to ask your question real quickly.
Hi. Yeah, I have a question for Hangi. So Hangi, when you show that if you remove the diabatic heating, the wave activity amplitude decreases. But from your plot, it also looks like the wave activity amplitude also shifts poleward with respect to the climatology. Is that interpretation correct? And why do you see that?
So I'm going to repeat this question again. So the diabatic shifted to the poleward a little bit. I suspect because in this model we go into a little bit of details about the model is suppose that the transport, the speed of transport of the wave activity stays the same. So so that when you're decreasing the positive part of the residuals, the drift speed is still over there. So I think it's partially leads to the answers that there are different locations of the diabatic sources and what exactly the wave activity decreases. So it's basically due to the transport effect of the wave. Yeah.
Okay, thank you.
Thank you.
Thank you so much to all of our virtual presenters. Let's give everyone another round of applause.
Hi, everyone. I'm Melissa Breeden. I'm co-chairing the session with Jen Liu. And this is the diabatic processes session and feedback session. And first up, we have Seraphine Hauser, who is at University of Oklahoma. Come on down.
All right, so thank you, Melissa, for this introduction. And yeah, I'm happy to kick off this diabatic processes and feedback session, talking about the contradictory results concerning the relative importance of dry and moist processes in blocking dynamics. And therefore, we have here a lead question, which is it a perspective that matters? And before I wanted to start here, I just wanted to thank you different people that contributed to this research that I'm doing or that I'm showing today. So I wanted to highlight Christian Grams, Michael Riemer, Franziska Teubler, Jan Wandel, Dominik Bühler, Julian Quinting, Peter Kniberts, Daniel Steinfeld, Volkmar Wirth, and Christopher Post, and many, many more. And I'm sure some people are familiar to you. So being the first talk in the session, I just wanted to draw some attention and give you a small introduction into like the different diabatic processes and the feedbacks we're looking at. So when we think about like the mass and heat exchange with the environment, we think about processes or subcategories like solar and terrestrial radiation. We think about phase changes of water species like in clouds and precipitation. But we also think about surface sensible and surface latent heat fluxes, and finally also turbulence and friction. If we think about the effects of diabatic processes on blocking, so we just take these subcategories and look what's already has been done in the literature, and starting here with solar and terrestrial radiation, there are some studies showing that there's an effect when we look at the upper tropospheric PV anomaly and like the effect of long radiative cooling. And we also will hear another talk about this in more detail later. We also can look at surface sensible and surface latent heat fluxes. And there has been some work done, especially in the last 3 years, by people looking more into like oceanic maintenance and especially the role of the Gulf Stream for blocking development over Europe. We then can look at turbulence and friction, but they are predominantly neglected. And one category that is kind of left over is the phase changes of water species, where we also see a subsequent talk. And this is also the part that I want to focus on today. So when we think about latent heat release in mid-latitudes, we often think about these warm conveyor belts. And although we have heard about them before, I just wanted to take a second to introduce them to you a bit closer. So when we think about warm conveyor belts, we think about strongly ascending airstreams in the vicinity of extratropical cyclones. And you can see on the left-hand side a schematic that kind of shows how this could look like. So you see on the surface, like this extratropical cyclone, we have kind of the inflow region of these warm conveyor belts. We have the maximum diabatic heating in the mid-troposphere, and then in the upper troposphere, we often have like this divergent outflow that can modify the large-scale flow through which amplification. And often we find those warm conveyor belts in the mid-latitude storm drag regions. When we think about the identification of warm conveyor belts, the traditional way is with trajectory analysis. And this follows the method of Burnley and Davis in 1997. So what they do is that they calculate either forward trajectories from close to the surface or backward trajectories out of the block, and then kind of uses criterion that an air parcel, in case of forward trajectories, has to ascend at least 600 hectopascal. And we can also look at the different stages of this warm conveyor belt. So looking at warm conveyor belt inflow, ascent, and outflow. However, as like trajectory analysis is computationally quite expensive, Quinting and Grams in 2022 came up with a novel Eulerian identification using deep learning. And this has also been mentioned by one of the poster presenters, which is called the Elias 2.0 method. So here we look at warm conveyor belt footprints from Eulerian fields, and we can also look at the different stages, namely the inflow, the ascent, and the outflow. Okay, so when we think about the importance of latent heat release for blocking in particular, there has been some key work done by Stefan Pfahl and colleagues, mainly from a Lagrangian perspective. And I just wanted to briefly highlight like the main findings in the last years. So the first kind of kick-off study on that was performed by Pfahl et al. In 2015, and they found that up to 46% of air masses involved in blocking in the Northern Hemisphere are heated in the days before their arrival in the block. And you can see that kind of in this schematic on the left-hand side, where you can see on the y-axis the PV anomaly strength, and on the x-axis kind of the heating strength. And the shading shows you the frequency density. So they came up with like different subcategories, and one of them that includes the diabatic heating showed that there is like 46% of the trajectories were heated before they arrived like in the blocking region. And this is shown for 3 days, but even if we include or even more days, then the amount of trajectories that are heated is even going more up. In a follow-up study, Steinfeld and Pfahl in 2019 showed that they're like moist diabatic blocks, and they develop faster than dry adiabatic blocks. They are more intense, they are larger in extent, and they are often long-lived. In numerical experience, they switched off latent heat release upstream of the block, and what happens is that you either get like a functional weakening of the block, or even like a complete elimination of the block, that it's not even developing at all. And in a most recent study of Steinfeld et al. In 2022, they show that with climate change, there's stronger latent heating, and that points to also to an increased importance of moist processes for future blocks. When we think about moist processes and ask ourselves the question, does it limit predictability? I just wanted to highlight one case study here. So it was a European blocking, and it was also a forecast bus for various numerical weather prediction centers. And it occurred in March 2016. And you can see in this upper figure is the anomaly correlation coefficient shown as a function of time on the x-axis. And you can see the sudden drop of predictability skill. And here the forecast bus was associated with the onset of a strong blocking over Europe. In a study led by Grams et al. In 2018, they could kind of draw back like this arrow in the forecast due to a misrepresentation of the warm conveyor belt upstream of Europe. And therefore, there was like an amplification and the propagation of the forecast error via the warm conveyor belt downstream towards Europe. However, also other people looked at this more in a systematic analysis. Here we look at warm conveyor belt activity and European blocking predictability. So using ECMWF IFS reforecasts in winter and looking only at blocking onset between lead times 10 to 15 days, Jan Wandel could show that first, like based on error interim, that we have an increased frequency upstream of the European blocking region in the 2 days before blocking onset. However, if they look at like false alarms, hits and misses, they could find like really strong differences. And one thing I wanted to highlight here is when you look at the hits, you can kind of see in this reddish colors, which shows you the frequency anomalies of warm conveyor belt outflow, that we have a lot of like an above average warm conveyor belt outflow frequency upstream of the European blocking. But if you look at the part that shows you the misses, you can see that this is completely missing. So forecasts that miss blocking onset over Europe don't have this increased warm conveyor belt activity upstream. Okay, so I talked about like just moist processes quite a long time now. So I wanted to bring it more into like a joint picture together with the more dry dynamics. And here we also compare different perspectives when I call like the Eulerian versus the Lagrangian perspective. And many studies investigated the role of either dry and moist dynamics, but they often result in contradictory results. And I just wanted to pick here one example to show you what I mean. So on the left-hand side, we see the Lagrangian perspective, and this is a figure of Steinfeld et al. In 2019, and it shows for different regions on the Northern Hemisphere, the latent heat contributions on the y-axis in percentage, and then for 3-day and 7-day backward trajectories out of the blocking region. And if you just focus on the 2 red boxes, which shows you for winter and summer, the latent heat contribution for blocking over Europe, you can see it kind of varies between 20 and 40% for the 3-day backward trajectories, and even up to 60, or from 60 to 70% for the 7-day backward trajectories. So based on this perspective, we would kind of conclude, okay, moist processes played an important role here. However, and this is shown on the other hand, on the other side here on the right-hand side, focusing more from a Eulerian perspective, and this is a figure that I got from Teubler et al. In 2023. So there we're looking also in a composite sense about like at a European blocking, and they were projecting different PV tendencies on blocking over Europe. And I just wanted to highlight here this red curve that shows you the tendencies and the contribution from moist dynamics. And you can see it's really close to 0, kind of pointing to a nearly negligible effect of moist processes from this perspective. So this kind of brings us to the question, how can we bridge the gap between the pure Lagrangian and Eulerian perspectives? And which puzzle piece is kind of missing to combine the 2 approaches in a joint analysis? For doing that, during my PhD time at KIT, I developed a quasi-Lagrangian framework and applied it to ERA 5 reanalysis data from 1979 to 2021. So the basic idea here is to combine both like the Eulerian and the Lagrangian perspectives by using Eulerian PV tendencies, but follow the PV anomaly linked to the block, which is the Lagrangian part. So it works as follows. So in the first step, we identify PV anomalies linked to blocking. So what we do, and this kind of follows the methodology of Schwirz et al. In 2004. So we look at negative PV anomalies in the upper troposphere. And when we think about the upper troposphere, we here take a vertical average between 500 and 150 hectopascal. We then calculate anomalies relative to a 30-day centered running mean climatology. And then we select a percentile threshold that varies with season, just to account for the strong anomalies in winter compared to summer. In the second step, we want to track these features, and therefore we use a novel tracking algorithm developed that is based on contour overlap. And one specific part of it is that we can also detect and handle splitting and merging event, which is a common problem when we think about feature tracking. And then in the third part, and this is where the Eulerian part comes in, we look at the amplitude evolution of our tracked PV anomalies. And therefore we look at the PV tendency equation that we also have seen several times now. So we have the local change in PV that is governed by the advection of PV and the non-conservative processes. And we further partition our full wind field into different sub-wind fields just to be able to look at different processes and how they kind of have an effect on the amplitude evolution. So we use Helmholtz partitioning to focus more on the divergent wind field, and we use piecewise PV inversion to make use of the wind fields associated with upper and lower tropospheric PV anomalies. We can rewrite it in an equation that describes the area integrated PV anomaly amplitude change, and this is done on isentropic levels. And we come up with different terms that I want to introduce now. So the first term here on the right-hand side that we short call the up term presents like the barotropic upper tropospheric wave propagation and wave dynamics. So we have here how like the background PV field is advected by the wind field associated with the upper level PV anomalies. The second term is basically the same, just that we're using the wind field associated with the lower level PV anomalies. So this is more the baroclinic interaction term. Then in the next step, we look at the divergent term that consists of two parts. The first part is the advection term that describes the advection of the background field with the divergent wind field. And the second part describes the divergence of the divergence wind field. And this part, so the second part, is often associated with warm conveyor belt outflow in the upper troposphere and its divergent outflow. We then also have like a residual term that describes the advection with a residual wind field. We have the non-conservative part and also a boundary part that takes into account that these PV anomalies can also grow and shrink in size. So we have a change in area as well. What we did is that we looked at blocking here from a weather regime perspective, which is kind of different to what we've seen already in this workshop. So we investigate blocking dynamics in different subregions over the North Atlantic European sector using the 7 year-round weather regime definition by Christian Grams. And we here look at when we look at the 7 year-round weather regimes, 4 of them are the so-called blocked regimes because they feature like a persistent anticyclone in this region. So the 4 subcategories of blocking we're looking at are Greenland blocking, Atlantic ridge, European blocking, and Scandinavian blocking. And you can see their patterns based on upper tropospheric PV anomalies and shading. And you can see in the black lines the absolute PV in the upper troposphere. So you can see there are quite some differences, not only like in the position where you can find a block in this subregion, but also in the circulation that this block is embedded to. And if we think back about our quasi-Lagrangian technique, what we do is that we match those PV anomaly tracks that kind of go through that regions and show like a spatial overlap with the block. Okay, so coming back to the case study that I presented before when we looked at the predictability of European blocking, we kind of selected this case to test this quasi-Lagrangian framework. So we look at this European blocking bus case that occurred in March 2016. We matched the negative PV anomaly track that was associated with the block. And what we can see here is shown in this figure. So we can see the track of these negative PV anomalies. And what immediately jumps into your eye is that this PV anomaly did not form locally over Europe, but had like a remote development over the Western North Atlantic. So this PV anomaly has like this non-local development and also developed in the days before we even kind of identified this blocking at all. What we can do then in the next step is to look at its amplitude evolution of these negative PV anomaly. And you can see the full lifetime. So this is shown on the x-axis. I marked again where we had this active blocking region over Europe. And you can see PV tendencies. So everything that's positive here points to a strengthening in amplitude. Everything that's negative points to weakening. And in the black line, you can see the total change in the amplitude. And what you can see is there are pulses of amplification before and also in the first half of like this blocking event. And this kind of raises the questions, okay, which processes were associated with these pulses of amplification? So I can put in like all these different processes that I explained at the beginning, but I just wanted to focus here on the processes that are linked to moist processes. And here we first look, of course, at our direct diabatic modification term. And surprisingly, we can only find a small contribution to the weakening of these of the amplitude. And this is dominated by long-wave radiative cooling, which you can see in the bar plot where I try to summarize the net effect of the short-wave radiation, non-radiation, and long-wave radiation. So surprisingly, we don't see like a lot of like a big signal here from this term, probably because we're integrating over our PV anomaly area, and you have like this direct diabatic processes on a really small kind of scale, so it kind of cancels out when you integrate it. But however, and this is what I mentioned before, we can look at the divergent outflow because it's an indirect moist component as it is linked to warm conveyor belt outflow in the upper troposphere. And you can see that here it leads the pulses of amplification before the blocking, but also during this blocking event. And therefore, we can kind of conclude what already has been shown by Grams et al. 2018, but more like in a quantifiable way here, that the divergent outflow leads the pulses of amplification and points to the importance of moist processes. Okay, but now switching like from a single case study more to a systematic investigation. So what we did is that we matched like all the, for each life cycle of Greenland blocking that we looked at, we matched the negative PV anomaly tracks and we're interested where are they located 4 days before the blocking onset. And this is shown here for Greenland blocking. So I kind of, you can see this blue kind of circle. This is where you will get your Greenland block once the onset kind of hits. And in shading, you can see the frequency of PV anomalies, and the black line shows you those that are block related. So what you can see is there are 2 hotspots. So PV anomalies are either located upstream or downstream before blocking onset. And this kind of motivated us to think about 2 different pathways of how these like more transient circulation anomalies get into the blocking region. So we came up with 2 different pathways. One is called the retrogression pathway, and it describes how PV anomalies retrograde from Europe towards Greenland, while we have an upstream pathway that describes more the northeastwards propagation from eastern North America into the Greenland blocking region. So one thing we also saw is that this is not only something that we see when we look at Greenland blocking, but this is also something we see when we look at the other 3 different blocked types. So if we look at the Atlantic Ridge regime, the European blocking, and also the Scandinavian blocking regime. So it's not a feature of the Greenland blocking. We kind of can conclude here our first key finding that PV anomalies linked to blocking over North Atlantic European region, they develop remotely with 2 pathways into the blocking region. In our next key finding, we were interested into the amplitude evolution. So what we show here in this lect composite, and it goes from -10 to +10 days. So the onset is in the middle where you can see the vertical line. And you can see on the y-axis, the isentropic PV anomaly amplitude shown here as an absolute value. And you can see that like it seems like all PV anomalies linked to blocking show an amplification in the days before the blocking onset. So kind of most of the activity or most of this amplification occurs before we can even identify the block. We can also find differences when we look at the pathways. So looking at the retrogression ones and the PV anomalies from upstream. So what you can see here is that the retrograding ones seem to have a larger amplitude earlier, but you can also see this rapid amplification of upstream PV anomalies. We were then interested again in the processes. So, okay, we have this amplification. So which processes are important here? And this is a composite for all the blocking events, independent of season, independent of pathway. And you can see in the black line and in the gray lines, the diagnosed versus the observed amplitude change. So you have this amplification before blocking onset and kind of the decrease that starts to occur after the onset. And if we look here at the different processes, I wanted to highlight this dark red line pointing to the divergent outflow term being the main contribution to this amplification. However, and here we focus at European blocking to make it more comparable later, we can also see how do the dynamics differ when we look at the different pathways. So you can see here the net effect of the different processes and the total amplitude change for the -6 days to +days around blocking onset. And you can see differences in the strength of amplification. So the upstream PV anomaly seem to amplify so much stronger than the ones that retrograde towards Europe. And you can see that mostly it's the divergent outflow tendency that has like the greatest effect on that. And if we think now about the location of Europe and thinking about these two pathways, we can kind of conclude that when you have like this oceanic pathway, you have a stronger effect of moist processes compared to when your PV anomaly moves over the continent. This brings us to the second key finding: with amplification of PV anomalies that occurs already before blocking onset is often dominated by divergent PV tendencies pointing to moist contributions. In our third key finding, we wanted to see then the link from this divergent PV tendencies and Wonken-Weyerwald activity. And here we used this novel Eulerian approach that I introduced in the beginning, and we looked at the activity of Wonken-Weyerwald inflow, ascent, and outflow in the days before blocking onset, because we saw that there's like this rapid amplification in their amplitude. So focusing here again on European blocking, we show here on the right-hand side a centered composite. So you see like the pseudo-lat and pseudo-lon. You have in the center of mass position of the negative PV anomalies, and you have you have like the black dashed and solid lines point to PV anomalies. And what is here of interest now is the shading. So we have Wonken-Weyerwald outflow in these more bluish, reddish colors, Wonken-Weyerwald ascent in the greenish colors, and the Wonken-Weyerwald inflow in the blue colors. And you can see nicely this kind of how a Wonken-Weyerwald looks like from a more theoretical perspective, and it kind of confirms what we know from theory. And also, and this is shown by these yellow contour lines, these are the amplifying divergent PV tendencies. So we have a really good agreement of Wonken-Weyerwald ascent and outflow and these amplifying divergent PV tendencies. If we compare this picture now to the retrogression pathway, we can see a completely different picture. So we have much less Wonken-Weyerwald activity for the PV anomalies that follow this retrogression pathway. And this kind of gives us a hint that it really depends on where the negative PV anomaly travels through, if it's like oceanic or more of like continental origin. And this brings me to the third key finding, that PV anomalies moving over the mid-latitude storm track region, they amplify much stronger by divergent PV tendencies, and this is linked to Wonken-Weyerwald activity. Okay, so we had some insights now into the quasi-Lagrangian thinking, but how can we connect it to results from pure Lagrangian or pure Eulerian studies? So starting with more the easier part, looking at the Lagrangian results, we can kind of see a good agreement with the Lagrangian perspective. So we have a large share of trajectories that are heated from a Lagrangian perspective, and we can see from the quasi-Lagrangian perspective that the dominant process is also a moist contribution. So we have this good agreement. However, comparing it to the Eulerian part, we can see that there's kind of a disagreement. But this is because of the remote moist dynamical development of the PV anomalies outside of Europe. And if we think about, and you can now focus on the more like light green and the light blue lines, these are like the dry dynamics. And we have our moist dynamics hidden in this dry dynamical advection terms because we have an advection of the PV anomaly into our blocking region. So this brings me to the summary. So we developed a novel quasi-Lagrangian PV framework to unify the separate Eulerian and Lagrangian perspectives on blocking dynamics. And I showed you some key results from this quasi-Lagrangian perspective using blocked weather regimes. So what we find is that there's a remote development of PV anomalies linked to blocking over North Atlantic European region and the propagation along the different pathways, so the upstream and the retrogression part. Then in the second point, the amplification of these PV anomalies take place predominantly before the blocking onset and is dominated by moist dynamics. And here we looked at the divergent PV tendencies mostly. And the PV anomalies moving over the mid-latitude storm track region amplify much stronger by the divergent PV tendencies than those compared like more of like a continental origin. So coming back to the question I raised in the beginning, is it a perspective that matters? The short answer is yes, it is. Because if we just focus more on the blocking region itself and we are not looking upstream and downstream, we might miss signals and some diagnostics cannot kind of catch these signals. So it's important to kind of broaden our horizon and to think about synoptic scale activity that can occur in the days before and also more remote of the blocking region, but have an effect in blocking development. So what we need is a combination of perspectives to yield a comprehensive understanding of blocking dynamics and the role of moist processes. With that, thank you.
All right, next up, we've got Zhaoyu Liu, who's from Purdue University.
Hello, everyone. My name is Zhaoyu Liu, and I'm a third-year graduate student in Purdue University, working with Dr. Li Wang. So the topic I will present today is titled as Blocking Diversity, the Distinct Roles of Diabatic Heating. So basically, the key question that we are trying to address is that where does diabatic heating occur in these two types of block, ridge and dipoles? And is diabatic heating playing the same role in these two blocks, or they are totally playing different roles? The answer to this question is very important because it can help us to better assess the future projection of the block. So the future projection of the blocking frequency is always a hard question because it's uncertain, it's hard to understand. For example, this is a classical future projection plot of the blocking frequency in the Northern Hemisphere winter season by Williams in 2018. So we can see that the blocking frequency in the Northwest Atlantic and Northwest Pacific is decreased, while the blocking frequency in the Northeast Atlantic and Northeast Pacific is increased. So how we can understand this pattern? So why block responds differently across different regions? So I think one of the gaps in knowledge is the lack of understanding of distinct dynamics among different types of block. So if we can separate block into different types and study them separately, we should find some new insight. So I will first quickly go through a literature review about the role of diabatic heating in iron block. And this has been a topic for a while, and these are all my favorite papers. So these 4 papers on the left, they are using the Lagrange tracking framework. They basically track the air mass finally into the block to show that the dry process and moist process basically playing a comparable role. And this case study about the 2021 Pacific Northwest heat wave is based on the local wave activity framework. It also suggests a strong diabatic heating source upstream to the block. So all these literatures are very important. They lay down the basic dynamics of the moisture in blocking system. And they overall exerts a positive effect on the formation and the intensification of the block. However, if you can separate the block into different types, we do find some different new insight. And this is a key message that we want to convey. So basically, we're trying to convey that the diabatic heating plays a distinct roles in different type of block. It plays a positive roles in ridge, while it plays a negative roles in dipoles. So here is our method and logics. So all the results are based on the MERIT-2 real-knowledge data set in the past 40 years. And I will also show some preliminary results from the CAMP simulation with fixed SST. So first, we will use a local wave activity framework to detect all the blocking events and separate them into ridge and dipole. So the local wave activity is a key variable that measures the finite amplitude of the wave in the block, which is well introduced by Professor Nakamura yesterday. So the ridge block refer to those block events only including anticyclonic components of the wave activity, while for the dipole block, it is referred to those including both cyclonic and anticyclonic local wave activity. So after we capture all the blocking events and separate them into different type, we will use a budget of local wave activity to quantify the contribution from a diabatic process. So first, I will show some basic feature of this two type of block. So like this figure is the geographic feature of ridge and dipole. It tells you where these two blocks are located. So we can clearly see that for ridge block, they probably located downstream to the storm track region, those red dots, and probably located at the northeast Pacific, northeast Atlantic, and over the Europe. Well, for the dipole block, those blue dots, you can see they are primarily located along the storm track region, is upstream to the region of ridge blocks. And for some other feature, you can see that the dipole blocks are less frequent than ridge, but for the duration and strength, dipole blocks are actually more persistent and stronger. Okay, so now we get to explore the distinct distribution of the diabatic heating in these two type of block. So this figure show the horizontal structure of diabatic heating, which is the shading is characterized by this temperature tendency due to moist process. It just tell you the strength of diabatic heating. So the contour is a 500 hectopascal gel potential height, and these are all the confidence patterns and at the peaking date of the block. So we can clearly see that for ridge block, diabatic heating occurs upstream to the block. This is consistent with all the previous work stating the importance of upstream lightning heating. But for the dipole block, we can see that the diabatic heating primarily occurs within the cut-low system, that is to the south and downstream to the center of the block, while the diabatic heating upstream is relatively weak compared to ridges. And we can find a similar result from the vertical structure of diabatic heating. And now the contour represents local wave activity, which maximizes the upper troposphere at the block center. So we can see that for ridge block, the diabatic heating again occurs upstream to the block, and it overall shows the homogenized structure from the lower to the upper troposphere, and it tends to stabilize the stratification. But for the dipole block, we can see that the diabatic heating is primarily centered at the lower level. It generates a strong lower to upper gradient of the diabatic heating, and it tends to destabilize the stratification. Okay, so now we get the distinct patterns of a diabatic heating into type of block. So the key question is how we can transform from the thermodynamics contribution to the dynamic contribution related to the wave amplitude in blocking system. So this is achieved by the budget of the local wave activity framework. So we can directly separate the contribution of the wave activity tendency by the diabatic process following this equation. So you can see that now we connect this diabatic heating term, dt moist, to this moist-induced wave activity tendency. It basically tells you to what extent the wave amplitude is changed by moist process. And so here's a good schematic plot to help you understand the calculation. And the basic idea is that the moist process is come with distinct diabatic heating in different type of block. And this is dt moist. And the QGPV field would be changed because it's no longer conserved. And then the wave activity will be changed as to the amplitude of the block. So to make sure our calculation makes sense, we make a comparison to the result with Neal 2022. They use a residual method to estimate the wave activity tendency by diabatic process. So this is their result, and this is our result. So we can basically see a consistent pattern indicating that our calculation makes sense. Okay, so now we explore the horizontal structure of this moist-induced wave activity tendency. So basically, it tells you to what extent and where the wave in the blocking system is changed by moist process. So the red indicates that the wave activity is enhanced by the moist process, while the blue means the wave activity is reduced by the moist process. So we can clearly see that for ridge block, the moist-induced wave activity tendency is positive upstream, while negative downstream, and is overall weak at the central locations, close to zero. It could be slightly positive or negative. So this pattern indicates that the moist process may not directly intensify the amplitude of the block at the central location, because the wave activity here is actually weak, close to zero. However, we do find a strong upstream wave activity enhancement, and this structure tends to shift the block upstream or westward. Is against the downstream propagation, so it helps to maintain this block to make it last longer. So we'll summarize is a persistent effect for ridges. However, we do find a totally distinct structure in dipole. So we can clearly see a strong damping effect at the central location, which can directly reduce the wave amplitude of the block. So this is totally different from the ridge. We can see a similar result from this vertical structure of this moist-induced wave activity tendency. The maximum is located upstream in the ridge and centers at about the middle of the troposphere. And for dipole, we can see that the dampening effect is centered at the lower level, but can extend to the middle of the troposphere, which can effectively reduce the wave activity of the whole column. So the damping effect is robust. You can also see this hypermolar diagram, and the contour is the wave activity. It's just tell you the composite blocking life cycle. And the shading is the moist-induced wave activity. So you can see that for ridge block, the role of moist process is only important before and in the early stage of the block is relatively trivial on the after part of the blocking life cycle. But for the dipole, you can see that this damping effect is very robust along the entire blocking life cycle from the beginning to the end of the block. So the persisting effect in ridge and damping effect in dipole is not only robust for this composite noise, but also robust for individual events. So here we will show the distribution of the dampening or intensification effect in two types of block, ridge and dipole. So this is a box plot indicating the domain average moist-induced wave activity tendency. It just tells you across the whole blocking domain to what extent the amplitude change. So we can also see that for ridge block, there's more than 1,000 events. The block amplitude could be either enhanced or decreased, but the overall change is relatively weak. However, for dipole block, we can see that the dampening effect of the wave activity is very strong. So entire distribution is almost shifted to the negative side. And this is also robust in this geographic plot. So the dots represents the location of ridge and dipole, and the color is represents domain average moist-induced wave activities, basically the intensification or the damping. We can also say that for ridge block, it could be either enhanced or reduced because there's both red and blue dots. And it seems like the enhancement is located at the Northeast Pacific. Well, for the dipole block, you can see that nearly all of the dipole events are featured by strong damping effect over the two oceans and even over the continent. And we can also show that the persisting effect is also robust for ridge. And so this is a persisting effect quantified by this west-east gradient of this moist-induced wave activity tendency. The large gradients mean that the persisting effect is stronger. So we can see that the persisting effect is more stronger in ridge than dipoles. And it's also clear in these geographic features. So now the color is represents a persistence effect. It's the west-east gradient of the moist-induced local wave activity. So we can say that for ridge, especially over the ocean, this persisting effect is very strong. While for the dipole, the persisting effect is relatively weak because of these light colors. Okay, so now we know the distinct geographic features of two-type block, and we also know the distinct roles of diabatic heating among these two-type blocks. So if we combine them together, they help to give some new insight to assess the future projection of the block. For example, the dipole is dominant in the Northwest Atlantic and Northwest Pacific along the storm track. And we also know that the dipole is experiencing a strong negative effect by diabatic heating. So if you combine them together, we can naturally think that we can naturally expect a reduced blocking frequency over the Northwest Atlantic and Northwest Pacific. And this is exactly what we can observe from this future projection plot. Similarly for ridges. So ridge block is dominant at Northeast Atlantic and Northeast Pacific, and ridge block is overall experience a positive effect from diabatic heating. And we can naturally expect the increased blocking frequency at Northeast Atlantic and Northeast Pacific. And this is also what we can observe from this projection plot. We admit that this is purely based on the diagnostic from the observation. More research is needed to quantify this effect in different hierarchy of climate model and idealized model. Since time is limited, I will just quickly go through the results from the CAM simulation. So basically, we find the consistent pattern for rage and dipole. There's a persisting effect for rage and a damping effect for dipole. And we are also trying to quantify this effect in the two-layer QG model based on the Held and Vapour configuration. Okay, so thanks for listening. This is the conclusion of this talk. So basically, for rage block, the diabatic heating occurs upstream, and it overall exerts a positive effect to persist the block. For the dipole, diabatic heating occurs within this cut low, and it overall exerts a negative effect that directly dampening the amplitude of the block. And more importantly, this provides some new insight that the distinct geographic feature of different type of block and the distinct role of diabatic heating, it can help to interpret the future projection of the blocking events. Thank you.
All right, next up we have Emily Neal, who is from Harvard University.
My name is Emily Neal. I'm a first-year PhD student at the Harvard Department of Earth and Planetary Sciences. But today I'm going to be talking to you about work I started while a research assistant at the University of Chicago in collaboration with Noboru Nakamura. I will also say, just as a preface, that I will not make a link to diabatic heating upstream until the very end. So it's a little bit of a different flavor than what I've previously focused on, but I am excited to share with you nonetheless. Actually, and I wanted to say the title of my talk before I move on from that as well. So today I'm going to be talking about the vertical structure of atmospheric blocking events, and specifically what we're calling the top-down thermodynamic control of atmospheric blocking on the magnitude of the surface heat extremes that we then see. So let's start with a specific example. Here I'm showing 2-meter temperature in late June 2021. On the 24th of June, we see 2-meter temperature looks about how we would expect, with maximums in the American Southwest. But by the 28th to 30th June, we have anomalous 2-meter temperature concentrated in the Pacific Northwest, and this is known as the 2021 Pacific Northwest heat wave. If we go ahead and draw a transect along 49 degrees north, right through the center of that region, we can see that warming was actually top down. So on the 24th of June, prior to the heat wave at the surface, you see a warm anomaly appear in the upper troposphere, slightly upstream of the heat event, with descent of isotropes over the following days until by peak heat wave around 30 June, you have this very tall, anomalously warm column of air over the heat wave region. So this heating from above, or this vertical temperature structure, is linked to the fact that, like many heat extremes in the mid-latitudes, the 2021 Pacific Northwest heat wave was linked with an upper-level atmospheric blocking. So on the 24th of June, we see the emergence of a ridge with maturation and slight shift downstream, 24 to 26. If we're saying peak blocking in terms of geopotential height, it would be 26th to 27th June with decay and then shift downstream starting 28th to 30th of June. So here's another way to look at the vertical temperature structure. On the left side, I'm showing, again, at 49 degrees north, but now at a point near the center of the heat wave, a vertical profile of potential temperature on these dates that I've previously talked about. For each profile, we can see 2 distinct regions, one in which potential temperature is constant, and that is your convectively mixed afternoon boundary layer. And then above that, potential temperature increases in the free troposphere. So from 24 to 26 June, appearance and then maturation of the blocking, we see again that our free troposphere is increasing, potential temperature increases, but now we see that it increases to the extent and to the depth that we have capped the height of your afternoon boundary layer to a lower altitude. And in the days following, you have initial warming of your boundary layer and then up to 12 Kelvin warming by the 30th of June, at which point we see the boundary layer exceed heights that it was previously. On this left panel, I'm showing the surface energy budget during this time. We see the dominant contributors are incoming solar radiation and then outgoing sensible heat flux from the ground. We don't see significant changes, say like a change from very large latent heat flux to a very large sensible heat flux. And so that led us to the question, what mechanisms set the maximum surface temperature during this event? And our hypothesis was that you have this warm anomaly set up by atmospheric blocking that suppressed convection. And so in the absence of these obvious diabatic contributions in a surface energy budget, the vertical temperature structure of your atmospheric blocking will matter greatly for the fact that we still get significant extremes. So in order to investigate this hypothesis, we're going to be using a tool called encroachment, which is the prediction of boundary layer temperature and height based solely on the thermodynamics. So for example, this is from Roland Stahl's textbook, Boundary Layer Meteorology. On the left, we have an early morning profile of potential temperature, and on the right, we have a heat flux over the course of the day. And so if we assume that the heat supplied to the atmospheric boundary layer goes completely into rapid mixing that then generates your late afternoon boundary layer, then we expect the area under this sensible heat flux curve or this vertical heat flux from the ground to be the same as the difference in area from your late afternoon profile and your early morning sounding. As an example, if I start with a profile that has a ground temperature of 290 Kelvin and a constant increase in potential temperature of about, I think I'm doing 3.5 Kelvin here, and I approximate a sensible heat flux over the course of 12 hours as a sine function with an amplitude of about 500 watts per meter squared, then my afternoon boundary layer change in temperature is a little less than 10 Kelvin. I think it's 8 point something here. And my afternoon boundary layer depth is going to be 2.5 kilometers. You can also then look at what happens if we say increase the sensible heat flux or increase your stability. So increase your change in potential temperature with height. What I'm going to point out here, this is what we expect, but suppose we fix a stability and we increase our sensible heat flux from the ground, we expect our change in afternoon boundary layer temperature to be larger, and we expect a deeper afternoon boundary layer as well. If we fix a certain sensible heat flux from the ground and now we increase our stability, we expect our change in our afternoon boundary layer temperature to be greater, but we expect our afternoon boundary layer height to be less. So let's fix at that 3.5 Kelvin per kilometer and a 500 watt per meter square peak in a sensible heat flux and ask the question, what happens when I introduce a warming in the free troposphere at a certain depth d? So my warming in the free troposphere here is this delta capital theta, and I'm introducing it at some depth capital D here. You'll notice that in order to do this, so the profile I previously examined is the dashed line. In order to do this, I now shift my upper profile, same stability in the free troposphere. But since I want to start from the same ground or surface air temperature, the difference there is going to show up as an increased stability in your nearer surface profile. For the same sensible heat flux, what happens to my boundary layer? I'm going to focus in on introducing a increase in your free troposphere potential temperature at 1500 meters or 1.5 kilometers. So if we look at, for the change in your afternoon boundary layer, if we look at that line at 1500 meters, then you see as you increase your warming aloft, you do see an increase in your afternoon boundary layer. However, if we go to this depth, something interesting that happens here is that your depth is not necessarily capped where you introduced a warm anomaly in the free troposphere. And so there is a dependence in these triangle shapes. If we look at 1500, if you go over to say like 5 Kelvin, you don't stay capped at 1500 meter afternoon boundary layer. Even though that's where we introduced a warm anomaly, you have to warm up to about probably a little bit more than 10 to stay capped at 1500. And that's where you get your greatest warming, is when we cap our convective boundary layer by introducing a strong enough temperature anomaly in the free troposphere. So here are those profiles that I just mentioned. So if we start with a morning sounding, where I've increased my free troposphere by 5 Kelvin at a height of 1500 meters, then I get an afternoon boundary layer that is warmed from what it was previously. We're now past 300 Kelvin. However, it's up to about 2 kilometers. It doesn't stay capped, but if I go all the way to 10, I can stay capped, and now I have more than 15 Kelvin warming from what I started at. So that is exciting in the sense that we can demonstrate this ability using really fundamental tools from textbooks to say that if you do introduce a strong enough warming aloft, we do expect that as long as it remains capped, that you can get significant warming just from the fact that we change your vertical temperature structure. However, our ultimate goal is to be able to test this mechanism in the presence of other things going on. So for example, what happens to your boundary layer overnight? People have speculated can then contribute to what your next day boundary layer is going to look like, as well as a lot of these events do have diabatic contributions at the surface. And so does this become negligible if we have these other signals going on? To do that, we've started to put together a 1D column model of the dry atmosphere. So we start with a ground layer. We've got a surface energy budget. We've got incoming solar radiation, incoming long wave radiation from the atmosphere, outgoing long wave radiation. And then this final term is our sensible heat flux, which is parameterized by the difference during your daytime ground layer temperature and your surface air temperature above. So whenever those are different, we expect a heat flux so that they are homogenized. Then in our interior, we link our ground layer to the atmosphere by the sensible heat flux, which we're going to represent here as a turbulent diffusion. Finally, how we actually build an atmospheric boundary layer is through the process I just talked about called encroachment. So whenever our ground temperature does become larger than our surface air temperature, we turn on encroachment. And so the boundary layer estimate of final temperature and height is going to be based on the area and energy conservation methods I just talked about. Then over the night, we turn back on a turbulent diffusion, wipe that boundary layer out. Sorry. Oops, wrong way. So for example, here's that profile I just did in our initial condition with a 3.5 Kelvin per kilometer increase starting at 290 Kelvin. But now I can show a diurnal cycle of boundary layer temperature. So in the sunrise or right at sunrise, you see that our ground temperature has been cooling overnight. You also see that I allowed a little bit of the atmospheric or the original profile to cool overnight as well. And then during the day, we're going to be building a boundary layer. We get to about 2.5 kilometers again. Then in these other panels, I'm showing that you have your difference in maximum ground temperature versus your boundary layer temperature, and that we get pretty reasonable, or we can do this with pretty reasonable heat fluxes. So if you remember the magnitude of those heat fluxes I showed you for the 2021 event, it's about an incoming solar radiation of 800 watts per meter squared and about an outgoing sensible heat flux of 500, 550 watts per meter squared. So we're doing reasonably well here. Then we can rerun these experiments. So I can start the model with an initial condition where I introduce a warming aloft of here. I'm doing 10 Kelvin warming at 1.5 kilometers. And again, I get a late afternoon boundary layer that's increased by more than 5 kilometers, or increased by more than 5 Kelvin and still capped at 1.5 kilometers. If I go ahead and introduce that same warming, but now at a lower altitude, boundary layer doesn't stay capped. We do get more than 6 Kelvin warming. I think it's 6.8 in this case, So your boundary layer continues to warm. However, we don't stay capped. It does agree with what we've thought about previously. So in summary, extreme heat waves in the mid-latitudes are linked to anomalies in the upper level jet stream. We do expect the vertical temperature structure or warming aloft to influence surface extremes. And how they would influence surface extremes is by influencing your convective boundary layer. Future modeling work will investigate the role of this top-down warming mechanism that we can set up very easily back of the envelope, but now in the presence of other processes, such as cooling overnight. How do those processes impact what your morning profile looks like, as well as changes to your surface energy budget. And then quick link, because I have previously done a lot of thinking about diabatic heating upstream, is that, as mentioned in the talk before me, we do expect those to change the stability of your vertical profile in these events that are linked to ridges, specifically upstream diabatic heating. Thank you.
Great. So if the rest of the speakers from the session could please come up for some questions. Great. Yeah, and people can feel free to line up with questions for our speakers. And just a reminder, if you're an online participant, to raise your hand, and Alyssa will flag that you have a question. All right, yeah, John.
First off, I just want to say for the students, you guys did an awesome job. Thank you for sharing your talks. It was really great. My question's for Seraphine. So I apologize if I misunderstood the experimental setup that let you answer this question, but I was wondering about how you know, it's kind of like a chicken and egg thing. So how do I know? I'll start with the easy one. So if I'm over land or I'm over the ocean, almost by construction, I have a frontal boundary over an infinite pool of liquid or not. Moist processes presumably are, going to be more important where there's water. But that doesn't tell me whether the one over the water in its absence, would have amplified differently than without those processes. Likewise, if I have a stronger block or not a stronger block, I have stronger frontal zone or not. And one would presume that, the strength of the warm conveyor belt kind of goes along, scales with that. So my question is how do I know whether those are just diagnostics of one another or whether there is a causal relationship? Does my question make any sense?
Yeah, I think so. Thanks for your question. And I think it kind of makes sense. So given that we have warm conveyor belts mostly like over the ocean basins, so it's kind of not surprising that PV anomalies traveling more over the continents do not have like this push of these diabatic processes associated with the warm conveyor belt. So I totally agree with that. But as you said, it's like a chicken egg problem. So I think what I wanted to point out and in general is that I think this pathway thinking is something that is quite novel. Just thinking about it, like the track of the PV anomaly kind of matters. So if we have like a PV anomaly that is induced like over the Western North Atlantic, and it is kind of propagating through the North Atlantic, like the chances are pretty high it is like amplified by moist processes more than when we think about, I don't know, rural blocking, for example, that is driven more by dry dynamics.
Whoever wants to go, some wrestle for it.
I also have a question for Seraphine. So you had a figure at one point, which was isentropic PVA, negative PVA. There's a little minus sign on the y-axis, and then lag days on the x-axis. And there was a zone that moved from about -6 days of onset to about 2 days of onset, where there seemed to be, rate of change, of increase in this isentropic PVA. This seems to me to be something that would be of interest in the forecast space, right? If you can see a rate of change that's that rapid, over such an extended period of time, 6 days is, something, that would be something that'd be interesting to key in on in terms of watching the evolution of a ridge or a block or, whatever the pressure system might be. I'd also be curious to know if forecast models, running out daily resolution, 6-hourly resolution up to 35 days could actually see that with any sort of, lead time, watch that development happen. So if you have comments on that, great. Otherwise, I just kind of wanted to say that sort of piqued my interest.
Yeah, so thanks for this question and the comments. I think that's a really good point and something we also thought about quite a lot too. How can we move from this era 5 reanalysis base? So how can we use it like for the prediction of blocks? And I think it's definitely not easy because the full framework is based on PV inversion, which is definitely not the standard output you have when you look at like climate model output. So yeah, I don't know what like the perfect answer is to that, but it would be great if we could find ways to kind of translate this framework in a kind of sense that we can use it for a climate model output. But something that I really wanted to highlight again is we have this unique warm conveyor belt data set, and that it's like a metric that is developed based on AI and can be used for climate model output. So this could be a good indication for where we can find moist processes and also, yeah.
And I'll just add to that phrase climate model, I don't know if you just mean that in a sort of general sense, or if you mean that specifically to say we're looking at temporal resolutions that are pretty coarse, like monthly, in which case I would agree with you, it's pretty challenging to see these things. But I would push on that for subseasonal frameworks for models where you're looking at, 6-hourly output, daily averages, and out to 35 days. So in the subseasonal space, I could see this having some interesting application.
Yeah, for sure. Yeah.
Cool. All right, we've got an online question.
Yes, please feel free to unmute yourself and go ahead.
Hi. Firstly, I would like to thank the speakers for really, really, really amazing talks in this session. I personally really enjoyed. I'm trying to connect some dots here. So this is a question to both Seraphine and Zhaoyu. It's interesting that you notice the difference between the two different pathways of blocks from the continental pathway and the oceanic pathway. And I wonder, Seraphine, if you see a different kind of blocks, like the kind, for example, how Zhaoyu noticed that you do get like a dipole type block and a omega type block, and then there is different contribution of moisture from upstream versus local, and you, Seraphine, also you touched upon that. And if you have any comments about it, and do you see any links between these two very different ways of looking at the moisture impact on the blocking? Thank you.
Yeah, thank you for the question. First of all, we designed this framework primarily for the use of blocked weather regimes. So that was our first focus that we set on. But we also started to apply it for more like typical blocking indices and typical blocking diagnostics. And we also look at different blocking types. I feel like we're in mid of the analysis, but we can kind of see already differences in the dynamics for different blocking types, and especially when we look at cyclonic and anticyclonic wave breaking linked to blocking. In terms of like the pathway thinking, I think it's just like a novel approach to kind of look at processes that occur remotely of the actual blocking region in the days before blocking onset. And we definitely have to look into more details to kind of determine the relative importance of dry and moist processes. But I think like to apply it to more like standard blocking indices is a good step forward. I hope this kind of answers your question.
Yeah, thank you. Yeah.
And I also want to say that, so I think this is a very good discussion about whether we need to like separate block based on different regions or different type. So it seems like different type, it has different physical mechanism, but different regions also have different mechanism behind. So yeah, I think that's good like discussion point probably in the future, like just combine the region and the types. We shall know a better we can get a better understanding of the block and its future projection. Yeah.
If I can just add one comment, if I may, regarding the two different block types, I myself did notice that the ridge block type tend to not last as long as an omega type block, and it seems to be consistent with what you showed, that your moist wave activity contribution tends to damp out the dipole type block, and just a consistency and which seems to match with what I saw. Yeah. Do you think that's one of the mechanism why the the dipole type blocks are maybe lesser in number and not that persistent?
Yeah, I think this is a good question, because I also noticed actually dipole, although there's a strong damping effect, but it's actually averagely lasts longer than ridges. I think this could be attributed to there should be other factors that also influence the persistence of the block. And for example, there's tons of dry dynamics behind. That should be I'm not sure, but I guess the dry dynamic could be the first order thing that determine the basic strings, persistence, and all the basic feature of block. But so this work is just to see that, yeah, just the pure moist related diabatic process, how that can help to either persist or dampen the block. Yeah, so this is what we are trying to accommodate. But I think it's a good question to see that the dipole is actually more persist. But I guess this should be linked to the dry dynamics. Thank you.
Yeah, thank you very much.
Okay, I have a question for Emily. So it's really cool you have a simple model try to explain the diurnal cycle temperature. And I wonder if you know some recent work by Yi Zhang, and she's trying to use similar idea to explain the upper limit of heat extreme. I wonder if your model actually helped explain this kind of evolution a little better, because her argument is some sort of scaling argument, but your model is dynamical, which may be able to give some more detail about what's happening.
Yeah, excellent question. That work is very beautiful, but yeah, absolutely. So their link there is 500 hectopascal temperature and then setting what can be your maximum ground temperature using the MSE framework. Yeah, one thing I think here that we're diving into more specifically is, like I showed, the strength of your anomaly needed to keep the boundary layer capped. I mean, certainly the ideas suppressing convection in hers and mine are very similar, but I do hope to be able to, like you said, expand on how it can be influenced by more than just, I think they look at soil moisture in your 500 hectopascal or temperature, but here, by making a column model, we have the ability to then investigate other processes as well. Yeah, so that would be the goal.
Talk about nighttime temperature, but you can also look at the daily max, and that may be also very relevant to heat extreme.
Right, so like how far you can go. Yeah, absolutely.
Yeah, thanks. Lots of great talks. So yeah, back over to the diabatic effects. I guess to latent heating. I guess in both of your presentations, I didn't really see the kind of latent heating effect that I expected, which is I'm sure my ignorance. But I was kind of expecting to see that essentially a kind of a vertical advection. So where your latent heating is kind of enhancing the ascent, and so it would, it kind of looks like a dry term in budgets maybe. But essentially just a vertical advection of low PV air from near the ground. So where is that in both of your kind of analyses?
I think this is a good question, because I think this reactivity framework is just it's only capture the basic feature of this moist dynamics, but it can't capture like the specific moist process like convection or some like large scale condensation, something like that. So I think you are right that yeah, we cannot capture this detailed moist process, and but it just gives a like a big picture of this how this moist process works in this two type of block. Yeah, but I think it's a good direction that in the future that we can really focus on the detailed moist process by running some like experiment model, for example, to really test how this different moist process like convection, like large scale condensation or other process can really contribute to the persistence and the strength of the block. Yeah.
I think from the perspective that we have it in two kind of subterms that we are looking in our amplitude evolution framework. The one part is the direct diabatic modification, really looking at kind of signals, but if we integrate it over the area of the PV anomaly, just because it's so localized, we kind of get rid of it in an area integrated sense. So we can just kind of only estimate it looking at divergent outflow as like an indirect effect out of strong latent heating. So it's more like the indirect effect that we can quantify.
Makes sense. Thanks.
So I had a few questions for Zhaoyu Liu. First of all, I was wondering, is your decomposition into the ridge and the dipole, is it conclusive? Because I feel like maybe some blocks will start as a ridge and end up as a sort of a dipole structure. So do you classify each ridge, each block into this or this? That's wait, I have a few questions. So that's the first one. And then your dipole one looked a little bit more like cyclonic wave breaking. So I was wondering if is it really more cyclonic or is it a mix between anticyclonic wave breaking and cyclonic wave breaking? And then, okay, maybe I'll let you answer and then I'll ask the follow-up questions.
Okay, thanks. This is a good question. So in this framework, so yeah, it's true that some block, if you really like look at the evolution, it could be like a ridge first, but it's to somewhat break and twist it to a dipole. So here we only capture the structure at the peaking moment of the blocking life cycle, like the date with the maximum wave activity. So if at that day the block is featured as a dipole, then we say it's a dipole. If at that day it's a ridge, then we say it's a ridge. And yeah, so for the dipole thing, it's actually complicated because if we just include cyclonic and anticyclonic, is actually mix all the like cyclonic or anticyclonic breaking events and also the dipole. So yeah, this dipole is actually the mixing of all the all this event. Yeah.
Thanks. And then I guess first of all, I was wondering more generally, like what is the usefulness of using the local wave activity as opposed to thinking about PV tendencies? Because then if you see like a negative tendency on wave activity, you don't know if it's contributing to the ridge or the trough, because it's mixing. So I was just wondering, and then also I just didn't really understand why you get a dampening from the diabatic heating in the dipole case, because I would just think that diabatic heating would create a minus PV tendency aloft. So I don't really understand how it contributes to the dampening of the ridge.
Yeah, these are all good questions. So I think first of all, based on PV or wave activity, so you can see that this moist induced wave activity tendency is based on the vertical structure of the diabatic heating. So it actually depends on the static stability and the vertical gradients of the dt moist. So PV, I think, I'm not sure like if you are just mentioning like on some specific level or other, but probably I guess PV just provides the change for a certain level or yeah, but for this thing is so we can't just focus on one level. So we should consider its 3D structure, and the gradient, the vertical gradient, is very important. And but I think this is actually also not very intuitive because I also don't understand how to really interpreted this damping effect. And yeah, we do see this like different vertical structure and the positive and negative reactive tendency. But it's true that I still can't figure out how to really physically interpret this damping effect. And yeah, yes. And any more?
Yeah, no,
Any more
that's all.
comments? Yeah, thank you. Yeah.
Thank you so much.
Yeah.
I think I have a follow-up question for Zhaoyu. So I think I was wondering what controls the preferred locations of this region dipole type blocks. Is there any role of moisture doing that? So maybe it's asking kind of chicken and egg problem.
Yeah.
Whether it started off as a rich type, and because of this moisture impact, did it turn into a dipole kind of structure?
Yeah, so I think if you look at the geographic feature, you can see ridge is located downstream to the storm track. This is actually consistent with all the previous work, because downstream to the storm track, the variability is kind of, like slow varying state. So it's conducive to the ridge kind of block. But I think probably the key mechanism for dipole is because of the wave breaking or this nonlinear growing of the wave. So it should be, I guess it should be highly correlated with the storm track region where the wave is propagating and growing. And yeah, so that's why you can see the dipole is actually located along the storm track region. It's upstream to the traditional, blocking regions. Yeah, so I guess it's just related to the probably cyclonic stuff and also the the wave breaking and the nonlinear growing, something like that. But we don't know the exact reason yet. We'll actually just focus on why dipole is located there, but not downstream is another very interesting question, and maybe I will focus on in the future. Yeah.
Thank you all for a great session, and I have a question for Sandra. So, as mentioned by Zaire, so the heating profile, vertical profile, really determines the PV tendency, and so I'm wondering, the cloud relative effects depends on the cloud type and the vertical distribution of the cloud moisture.
Yes, exactly. So I mean, if you look at the previous slide, I think Kevin Grace is here. So it really depends on the type of the clouds. The cloud relative heating from the low clouds tend to lead to a decrease of the EKE, and the high cloud relative effect heating tends to increase the EKE. So the problem is that now in the models, because I think the previous study looking at the southern hemisphere, and then we are looking at northern hemisphere. But I think there is a recent study by Eike Voigt, 2023. They try to reconcile these contradictions, and I think the conclusion is really depending on the model, whether your model is with more high clouds versus low clouds, because it can have different impact on the EKE and baroclinicity, and in the end, affect your blocking frequency. It seems like, I haven't checked in a 3SM model, it seems like maybe we have more high clouds compared to low clouds, probably. So.
Hi, this is sort of a question I think for all of you. I know we're going to have a session about this tomorrow, but the brain trust we have assembled before us now, I think, might have some good comments as well. How, Zhaoyu, you sort of mentioned earlier about how the differences in blocks across different regions will be important. How much do each of you think that's related to, for example, the, alphabet soup of various modes of variability? INSO is sort of a global thing, but there are plenty of modes like the NAO or insert favorite mode of variability that will impact. How much do those influence some of the work that you've presented here? How generalizable, I suppose, do you think?
I think first of all, like for the, I guess for the ridge type of block, they are located downstream to the storm track region. I think this should highly correlated with like the baroclinic inner mode, this kind of slow motion variability of the atmosphere. But like for dipole, is located upstream, it's all along the storm track. I'm not sure which kind of large scale modal variability could connect to that.
Hi, I have a question to Zhaoyu. Thank you for your talk at first. I'm interested in the future changes or the perspectives in your opinion? In your talk, the dipole blocks, for example, the dipole blocks could be dampened due to the moist processes related to the diabatic heating. Does it suggest that the dipole blocks would be dampened if the diabatic heating increase in the future?
Well, this is a very good question because, yeah, if I think this this only works if we really find that with more diabatic heating, there's more damping effect. We haven't really dived into the detail about this relation, but I guess it's doable that we can perform some experiments like by uniformly increase SST, so that we can focus on the role of diabatic heating, and we can see if diabatic heating is increasing, and we can find a stronger damping effect or negative damping effect. Yeah, this is a good direction to go, and we are actually just currently working on that, like using CAM, and probably in the future conference I will show the new results based on this climate model. Yeah.
Great, thank you.
Hi, first of all, very great session. And this is Zheke Li from University of Pennsylvania. So I probably also have a question for Zhaoyu Liu, and because I know your work, the role of the diabatic heating actually have a like damping effect in the case of dipole black blocks, but kind of have an enhanced effect in the case of the ridge blocks, and this is really generate intense interest. I think either like in the audience here or online. So I just would like to open up another possibility, like for this kind of phenomena. Is there any? Have you ever looked at if there's anything to do with the while the moisture has been injected into the blocks, whether it is injected underneath the blocks or it kind of injected upstream, probably in the western flank of the blocks.
I think based on the vertical structure, we can find that like for ridge block, the moisture is actually injected just upstream, and actually it's very homogenized structure. Upstream is from the lower to middle troposphere is kind of in the same strains about the moisture and the diabatic heating. But for the dipole block, the moisture is probably just centers at the bottom level, around like 850 hectopascal, something like that. So to some reason it cannot penetrate to the middle of the troposphere, and yeah, it's for dipole is only at the bottom level. Yeah, thank you.
We have an online question.
Ping, go ahead.
Yes, thank you. One question also for Zhaoyu Liu. I missed a part of your talk. Maybe you have explained my question already, but let me ask the question first. So you mentioned that you use the peak phase is characterized by largest wave activities. So I'm thinking whether this largest wave activity can be used to separate the different types of blocks. In your case, will be ridge type and dipole type, or in other words, in these two types of blocks, how different would the wave activity be characterized? Are they the same, or are they different? In what sense?
So first of all, like dipole, the average strength of dipole is stronger than the ridge. And you can imagine that because it's a more twisted nonlinear structure of the wave, so it's stronger. And for the detection, it's true that we focus on the peaking date of the block, and if at that peaking date the structure is a dipole, then we see the dipole. If at that peaking date is ridge, then we say it's a ridge.
Okay.
Hope this answers your question.
Yeah, maybe I should ask in a different ways. I think the wave activities, there's some numbers to characterize that, right?
Right. You mean the threshold?
Yeah, I mean, since it's a peak, the wave activity should be very large.
Yeah. Yes.
Yeah. Okay. Can we use that amount of wave activity to as an index, for example, to separate these two different types?
Oh, I think this. Yeah, I actually look at the individual ridge and dipole events, and it's hard to really generalize that. if it's beyond a threshold, then it's dipole. If it's under threshold, is it rich? So I think it's better to just separate them based on their wave structures.
Wave structure.
Like either from this like wave activity framework or from some like statistical clustering framework. Yeah.
Okay.
Thank
great.
you.
Thank you.
Probably have time for one more. If you guys want to fight about that, sorry.
I have a question for Emily and also for Sandro. So I think we learned all kinds of different diabatic heating, and I think that they appear to be instrumental for block. I wonder if you were to, let's say I'm a layman, can you give me a simple conclusion? What are the first order, what are the second order, and what are the things that appears to be very hard to simulate in the model? What are the challenges we're facing? So I wonder if you guys can share some insights into that.
So I think in terms of clouds, I think the model still has some difficulty to realistically simulate the clouds, right? And also, I think that I mentioned earlier, the clouds can have two effects. You have a radiative heating effect, and also it can also modulate the latent heating through the evaporations. And in my results, because since we output all of the different heatings, so we can quantify how much is coming from condensation, how much coming from the short wave and long wave. And it turns out when we remove the cloud or when you lock the clouds, the conventional heating is played a major role in contributing to enhanced diabatic source of the wave activity. And that the result we found is that it really affects significantly the frequency climatology of the blocking over the Euro-Atlantic sector. Yeah.
I guess what I immediately thought of was for the 2021 event specifically, a lot of studies have done kind of forecasting, so we can look at where you get these predictability jumps. And the predictability jump for the 2021 event was the warm conveyor belt event that we identified in our local wave activity analysis. So I think definitely modeling wise, when they get the moisture right, then they end up getting actually the temperature anomaly fairly well at the surface. So interesting.
And also I want to add something is, so for instance, if you change the cloud distributions and with and without cloud, so you not only change the conventional heating and the fact that diabatic heating, but you also can change the static stability at a lower level. That may also in fact influence your eddy growth rate and barochronicity, and EKE in the end is also affect the blocking. So it seems like in my cases, clouds play an important role, not only in the upstream region, but also in general for the source of the baroclinic eddies.
Great. Thanks everyone for the discussion. Let's thank our speakers again.